Tell me when. Okay.
Go ahead.
So, welcome everyone. Thank you for being here. We have a lot of people to thank, mainly first the CNAM, so the institution we are in. It's a school mainly aimed at people who already work, so that's why the courses happen mostly after hours, between 6 and maybe 9 at night. This is a school, so please, when you are in the corridors, do not shout, do not laugh too much. So if you want to speak, stay in the room or go to the coffee room, which is at the end of the corridor, where you can actually eat and drink. Do not use those right now. They're going to be put during the breaks in the break room, and then you can eat over there. If you're going for a smoke, please be mindful of the people working around you. Maybe go into the street and come back. So thanks for the CNAM to the CNAM for hosting us. The lady who could have given a few words is ill, so maybe she'll speak later, but she's not available right now. Thank you as well to the museum. We're going to the museum tomorrow night, and they are hosting us not for free, but they are hosting us at a time where groups are not supposed to be here, so they are doing us a favor. If you want to join us to the museum and you haven't bought the full package, we have some room left, so if you're a speaker you get priority, and then if we can host up to 25 people. So if you want to come to the museum, please do. The more the merrier. Thank you to the authors, to the program committee, to the Plan 9 Foundation, and thank you for coming. You have the schedule on the proceedings. Please notice that there is a space for lightning talks. So far nobody has registered for that. I think when the time comes, you can just come to the board and just show whatever it is you want to show us. We had some last year. It was very fun, very informal and very productive. There is a paper in the proceedings that will not be presented. It's Alisa's paper, it's at the end. It's an interesting one, and there was some chatter on 9 fans about it. So I encourage you to read the proceedings, because you will get some information that you don't have here, because she could not be here to present. Be mindful that on Sunday we are not here anymore, because it's Sunday is not supposed to be a working day. So we are moving somewhere else. The address is in the proceedings. Please do not come here on Sunday. You will find nobody. On Saturday morning there is a board meeting. It has not been put on the schedule, but it has been announced on 9 fans. So if you are here at the beginning of the hackathon, there is an open meeting of the board, of the Plan Foundation board. And there is a project to run a peanut gallery. I don't know much about it, but stay tuned. Maybe we will get online sometime. It's on Sunday, or? Maybe on Sunday.
Just informal hangout.
Okay.
Just online with some of the people who couldn't attend in person.
Cool. I just wanted to make sure you were aware that the social event, the museum visit, which is a guided tour of the museum here, do not include a dinner. You need to take dinner afterwards on your own time. At 6, we should vacate the room, because courses can be happening here. So we will need to put the chairs back and the tables back where they were. And you cannot leave stuff in the room, because if you do, people can come and take it, because we leave the room at 6 and it cannot be locked, because it can be used for courses. Sorry about that. For lunch, most of you have chosen to have lunch with us. Those who bought the 125 euros package, dollar package, the lunch will be paid for by the foundation thanks to your income. And those who didn't, you need to pay 30 euros to the restaurant. And the deal with the restaurant is you can choose one main dish and you will have one dessert. Same for everyone. That way it's quicker and we can be faster back here to share stuff again. I took your dietary restrictions. If you have any question, please come to me and tell me, and I will inform the restaurant. Make sure they understand. Please mind the time of the breaks and come back at the correct time. All the talks are going to be recorded and broadcast. If as an author you don't want that, please tell us before we start broadcasting your image. Also, at some point, we may take a picture of people being there. We will tell you when we do so. So if you don't want to be in the picture, just leave the area that is being recorded. And if you stay, we will assume that you are okay with your picture being taken, and maybe the photo going on social media saying that Plan 9 is awesome, okay? The toilet is down the hall that way, so you go out bolt, do a right on the left, and it's on the left side of the corridor. Please do not drink or eat those nice pastries. Thank you, David. Because they put like crumbs everywhere, so wait until they are put in the break room. That's it for me. It's a lot of info. I'm sorry about that. I will let Ron introduce himself.
Okay. Yeah. So I thought I'd say one or two things about the foundation, which is the force behind having the last 3 years of this conference, which we kind of brought back from dormant. So we had 2023 in Waterloo, 2024 in Philadelphia, 2025, of course, here in Paris. Thank you, Edward, so much for all the work you've done. And we hope to announce the 2026 location at the end of this conference. So Foundation is 5 years old this fall. I think two of the key people getting it started are here, Skip and Anthony. And I just wanted to say the first few years were just getting everything stabilized and becoming a 501c3, meaning we could accept donations. We were in that tax deductible category, getting the source back from Nokia, and they were very helpful and gracious in making that happen. We're working to get the trademark back because Nokia actually let that lapse, which was a bit of a shame, but we're going to get that done. And so the last few years have been about just sort of stabilizing things. We got moderation on 9 fans, that kind of thing. And I think in the coming years, we're going to look to trying to grow the amount of money we have coming in. I've actually had a talk with someone in the US, and they were talking about actually giving us some pretty decent funding, and also try and find places to host systems. We'd like to find a couple of labs to host systems, at least in Europe and Canada, we're looking at. And I've actually talked to companies that might be willing to donate systems to us because we are a 501c3. This is an old joke that's called selling it to Uncle Sam, but if they can donate hardware to us, they can write it off on their tax return at full cost. So we're looking to get some donations of equipment in the coming year. I'm going to show you an interesting potential system, though, that we might be able to get to do testing of 9 front at scale on modern HPE server hardware. So I'll talk about that. The last thing I wanted to do is thank Skip and Anthony. And you know, Anthony has just worked tirelessly to get us financially sound, to get us to be a 501c3, which was just an exhausting slog with talking to lawyers all the time. You wouldn't believe how hard that is to do. So, you know, if you get a chance, go over to Anthony and say thank you, Anthony, for 5 years of very hard work on just this deadly dull work of getting the foundation to be what it is today. It's just been great. So I just wanted to thank Anthony. And Skip's been in charge of the IWP9 series, you know, and he's done a great job with getting, again, nobody ever reviews papers on time. Nobody ever submits papers on time. You know, nothing ever happens on time. And Skip is always very calm and makes things happen. So I just wanted to thank Skip for getting this thing. And again, Edward, I hope you'll thank CNAM. And of course, Daniel's here running our audio every year and making shit happen. So that's good. And then finally, our next speaker is Ron Minnick, and he's going to talk about VMs as threads. So Ron's been working with Plan 9 off and on for about 30 years, and his most recent accomplishment includes introducing himself as the next speaker. So, and that's the second time in my life I've gotten to do that. So I'm talking about VMs as threads, and what does that mean? Because a lot of you have probably used virtual machines with QEMU and KVM and Beehive and stuff like that. So what does a VM as a thread really mean? And so my title slide here, I actually have the example. So this is a 3-line libthread program that runs on Plan 9 that starts a VM. And there's a couple of things to notice here. So the first thing, you have to call VM thread init to use this library, because what actually happens when you call VM thread init, it establishes when you create a VM that there will be a low part of memory that is copied, not shared, when you create that VM. So it's kind of like fork. And then there will be a high part of memory that's shared between all the threads and the guest VM. There's reasons about why I have to do this, but no need to get into them here. But in this case, I'm establishing that the first 16 meg when I create the VM will be copied, to the VM memory space, and the top 64 meg will be shared. So that's step one. So I've initialized this library. The next thing is I've declared br dot, which is a 2-byte array, which is the x86 jump to dot or infinite loop instruction. So this is relative branch, and then this is go backward 2, and when you're done fetching this instruction, of course, you're pointing at this byte, which isn't there, and you add 2 to PC, and you come right back here. So branch dot is infinite loop. The next thing I do is I do a VM thread create, and this is like completely following, the lib thread model, and I'm giving it a pointer to branch dot, and there's no argument, and the stack is that size. So what happens here? This is in my program, right? This is a piece of my program. And you always need to be able to load a VM image before you start it. And in all the other systems, it gets really complicated to do that, okay? And so in this case, I've taken a piece of my program and I said, I want to run that piece of program in a virtual machine in ring 0. And it turns out it'll start off in x86 real mode, so 16-bit mode, and that will become a VM. So this is by far, oops. So I've been working with virtual machines a long time. I starting with Zen. I did the port of Plan 9 to Zen back in around 2002 or so. I worked on a VM system called gvisor. If you've uploaded a YouTube video anytime in the last 11 years, that is the virtual machine system that runs an encoder and a virtual machine guest and encodes it. That saves untold billions of dollars running encoding software in Google. The fact that we had this virtual machine, it could suspend and resume. So I've done a lot of work with virtual machines in the last 20-odd years, and this is by far the easiest way I've ever had to run a virtual machine. So I don't know why the display went away. Oh, it's the Mac's fault. Oh, I thought it was some other problem. Okay. Apologies. I didn't realize that the Mac was wrong. So let me quick review what a virtual machine is, because it's sort of important to this. So here on the left I have a process, and there on the right I have a VM. What does a process have? What does a VM have? So a process and a VM have memory. It's got a memory image. It has registers. It's got a proc structure entry for it. It has a page table. You have to have a page table. I'll get into why in a second. And then additionally on Intel and on a lot of these others, Intel calls it the virtual machine control structure. It doesn't matter. There's always like this blob of memory with additional bits of state you've got to have because you're a virtual machine. And, process is can exit involuntary or voluntary, right? You get a trapper system call. VMs can exit involuntary or voluntary. It's called a VM exit. It comes with a lot of bits of information and registers. So, VMs have a little more state. Actually, compared to the size of a VM image like a kernel, that state is like noise, right? So they have a couple of kbytes of extra state. And the page table for a VM is mapping guest virtual machine physical addresses to host machine physical addresses. So in a VM, you have sometimes virtual addresses in the VM, sometimes physical addresses, but virtual machine physical addresses need to be mapped to host physical addresses. If you think about that for a second, you can tell why. You would not want to allow a virtual machine to just randomly map memory anywhere in the host, right? So you've got to have that layer of virtual machine physical to host physical. They're actually really similar, right? Why does it look so different and difficult on things like Linux? Why is there dev KVM? Well, I was at Ottawa Linux Symposium in 2007, and this comment came up. Why was KVM offered as an out-of-kernel device initially? And it turned out there was a little bit of politics on how that could be integrated more directly into the kernel. And so out-of-kernel was about the only choice they had. So what's different? So when I started at Google, I would meet with Prasad and we talk about stuff like this. And Prasad's comment is we have a virtual machine. It's called user mode, right? And that's actually a fair comment. And we kind of forget how weird it is that all our processes have address 0, right? That's kind of a virtualization of the address space. And if you go back long enough, if you're old enough, you remember when not all processes had address 0, right? They had all kinds of different addresses because you didn't get virtual memory. So that was actually a pretty unique thing. But where I think it's not quite fair is virtual machines can do a lot of stuff that you can't do from a process. You can set up page tables, right? You can take interrupts. The virtual machine guest can create processes of its own. And even beyond that, virtual machines can run in modes that you can't run the host in, like x86 16-bit real mode, right? I can run a virtual machine in that mode. If I ran the host in that mode, I wouldn't have a kernel anymore. more. So virtual machines can do stuff that you can't do in a process. And it can do things kernels can do with restrictions, and I wanted to touch on that a little bit because it's a point of confusion. So here I'm looking at paging. At the bottom I have a kernel with virtual addresses, then it has a page table that maps the physical addresses, and that's how you get the memory. That's why kernels always have a lot of things, the actual base address of your kernel is F8 followed by 14 zeros on an AMD 64. So that obviously you don't have that much memory. We may wish we did, but we don't. And so, that gets mapped to low memory addresses. So that's that. And then in a process, you have virtual addresses starting at 2 million in Plan 9 for AMD 64, hex 2 million because you don't get page 0. And that maps to physical. But if we think about a VM may have page tables internally, but VM physical addresses get mapped to host physical addresses in this thing. Has a lot of different names. Intel calls it the extended page table, I think. I like the name external page table. It doesn't matter. The kernel, though, the host kernel manages that thing on the right, and the guest kernel, if it has a page table, manages that thing on the left. Now, if you go and read the RISC-V, actually the RISC-V hyper design is beautiful. I recommend reading it. It's a really good design, actually, especially if you're kind of used to what happened in the x86 world. But they have this real interesting quote, which I elided a bit of. For any virtual memory access, the original virtual address is converted into a guest physical address. That's this table. And then it's converted into a host physical address. That's this table. That sounds simple, right? I just walk a page table, then I walk a page table, and I'm done. Well, that's wrong, actually. And I talked to the people who wrote that text, and they said, yeah, we left a few bits out for brevity. But now, when I take this address to that address, I walk through 4 PTEs, page table entries in that page table. And I map bits of the physical address to a page frame number, which is the physical address. So I take a virtual address, I go through the page table, I map that to a physical address. That physical address is the physical address of the next thing down that I'm going to map through, right? But wait a minute. That maps physical addresses to those. So what does a page table really look like? It looks like this. So I go to my guest page map level 4, I map that through the EPT to memory. I come back around to the 3. I map it again. Okay. So we started calling this the two-dimensional page walk. That's a lot of references. Okay. And in fact, a lot of people who do this commercially know that if you can make this use gigabyte PTEs, you can chop out the bottom 2 walks because you'll stop right here. And the other thing you can do, if you can make the external page table gigabyte aligned, you can chop out that part of the walk. So this is just something to keep in mind because this is kind of an overhead that a lot of people, I know I wasn't aware of it until I really looked. Yeah.
TLBs there.
Huh?
Yeah, TLBs.
So TLBs, yeah, the TLB helps a lot. But actually a TLB maps a virtual to a physical, and that physical goes through here, and then there's got to be a TLB on the host side. It's kind of a headache. So what we did in 2015, I ported 6 different virtual machine devices to Acros. We had Acros, which is a research kernel from Berkeley. We were evaluating it at Google for use in our data centers, and we knew we needed virtualization. We were going to host Linux as a guest. Acros had the hardware. Linux was our guest. It would be the full Google data center stack as a guest of Acros. So we were trying to figure out how we're going to do virtualization, and I ported these 6 different VMs to Acros and tested them, and they were all really unsatisfactory, right? So we did KVM, we did Beehive, we did a couple you never heard of, I did gvisor, and they were all complicated, and they all required me to bring in a lot of extra mechanisms because they worked as a device. And so we were talking one day, and I said, why are they different? Why is the process in the VM different? And we realized they're not. They don't need to be different. And so we made a process and a VM actually be treated the same way in Acros. The key idea is that when I am in the kernel and I'm about to resume a process, or a thread actually, I decide whether I'm going to resume that thread in a virtual machine context or as a process. And it turns out it's actually not that complicated to make that decision and take that step. So this is an old slide from an old talk. I actually tried to figure out, well, how much overhead is it at Acros to do that? It's about 2,500 lines, but it kind of gets scattered because now that VMs are processes, there are decisions that appear in a couple different places. So I just said, it's 5,000 lines. And then we had about 12,000 lines in the user libraries because in Acros, threads are scheduled in user context, not in kernel context. And then finally, I had a virtual machine monitor, and that was 600 lines of code. 600 line of code, virtual machine monitor was good enough to boot the full Google data center stack in a production machine in a data center. And the scheduler at Google, which is called Borg, did not know, right? It complained a little because it said, I'm missing 2 cores. I mean, I know how many cores this machine should have, and 2 of them aren't there, and I don't know why, but I'll keep running anyway. Just wanted to let you know I'm missing 2 cores. Those are the 2 cores running Acros. So this can work, right? And we sort of showed in a data center sense that it can work. And it was fast. So a lot of times we would say, all right, let's run this VM guest on Acros, right? And we'd say hit return, and we get a prompt, and we say, it failed again. What's wrong? And then we would look a little more and say, oh, we're in the VM. It was just so fast we didn't realize that we were in the VM, right? It was like literally almost as fast as a process fast. And it had a lot of other cool attributes. You could put a virtual machine in a pipe, right? You could do a lot of things. And it was just the best virtual machine environment I've ever used. And of course, if you've ever looked at QEMU, I mean, there's a tool called KVM tool for Linux. It began life as 5,000 lines of code, and everybody was amazed that you could do it in only 5,000 lines of code, and this is 600 lines of code. So, and another thing happens. Remember I mentioned there's a page table and a page table for virtual machine? Slightly different thing. If I say a process and a VM are the same thing, I have a process page table, because I'm going to be a process. Then I have a VM page table. So you think about the proc struct, and I've got a process, I've got a thing that's going to be resumed as either a VM or a process. They're going to have different page tables. It's even better because on Intel processors, the external page table format for a VM is an Itanium page table format. Don't even try and understand why that happened. Nobody's ever figured it out. By the way, the IOMMU on Intel processors, the page table format is also Itanium. So we had this, right? I'm going to be a process, I'll use the process page table. Oh, I'm going to be a VM, I'll use the VM page table. Oh, I need to change it? I had a fault. Got to lock this, then I've got to lock this. Oh, shit. Okay, or I had a fault here, I got to lock this. Oh, but if I'm going to change this, I got to lock this. It was a nightmare, right? This was a really messy thing. You can find a pretty nice write-up in the Plan 9 source that involves a similar kind of nested lock mess. And it's a good read. Russ wrote it, I think. So go look for it. But it was 2 locks, 1 large headache, and then I kind of realized something during a talk we were having. I can take and have 1 lock if I pair the page table pages for the VM and the process. So what I do is, for every page table page, I pair these in an 8K thing, okay, a double page, and the low half of it is for a process, and the high half of it is for a VM. And now if I fault in the VM, I just subtract 4K from my faulting address and go here, and I can find out what the PTE ought to be. So this just broke open the whole mess of dealing with this. Now I've actually implemented this in 9 front actually, and I've implemented it as a boot time switch. I don't like if, defs, and kernels, and it turns out to be fairly simple to do. It was fairly simple to do in Acros and fairly straightforward in Plan 9. And what's nice about this is page table root is loaded from double page plus 0, and the guest page table root is from double page plus 4K, and this sort of 4K plus or minus just makes everything just dramatically easier. All right, so what did this look like in Acros? Everybody's used to pthreads in the Linux world, so we did it as a pthread-like model. So here is the manager, and here is the thread. And we have a struct called a virtual machine, kind of like you have a struct called a pthread struct. And here's a static called count. And when we set up VMs with attr and init, like to pthreads, we have attrs, so we call VM pthread pattern init, pointing to that thing, and then to create a thread. Again, like pthreads, you call it with the pointer to the VM. There's your ID, and there's the function you're going to run as a VM. And this loop is just waiting for the number to be incremented to 1,000,000. My virtual machine, it does while atomic add. It does a VM call to give a little bit of delay. And here's another thing you do in a VM you can't do in user mode. You halt. That's the exit. So thread join can be a halt, right? You're allowed to do that. Notice this is one program, right? This is a .c. It's just that when I start a VM, I can start it the way I did with POSIX by saying, here's a function, put it in a VM for me. And also notice, in this case, in the VM, there's no kernel. So this is running at ring level 0 right in the guest. You can do that. So you can put programs in VM guest that don't have a kernel with them, which is really very nice. You can also do things like put your ACPI or your system management interrupt stuff in a VM so you can test it. And driver VMs are very easy, right? So you can make a VM that's just a driver. All right, now I'm going to touch on the Plan 9 VMX device. I really like it. It's worth, or I should say 9 front. I think it's actually quite a nice design. So 2260 lines, that's pretty impressive. And the way they divide the responsibility between what you do in kernel and what you do in user mode, I thought was particularly well thought out. So there's a device, the hashx device. You open hashx clone, same way you do with everything else in Plan 9. It gives you a link to a CUDL or an FD for a CUDL file. You can read your ID from the CUDL file is the first thing you do. And then you just run this event loop. You get a couple files, CUDL status, regs, FP regs, map weight. Map is this thing you read to see how you've mapped memory for the VM. Weight is the key one here. And status, you can just read for status. So basically, this libthread thing runs this VMX thread, and this proc sits and blocks on reads from that weight. And the key thing to remember, with the process, you read the weight and you get an exit status, and the process is gone. With a VM, you read the weight and you get a VMX status. You can resume it. So that's what's a little different. So you read things and you get strings like this. And in this particular case, the period means there is an instruction, not a type of instruction, but an instruction. Because you can have, if it didn't have a dot, it would be a kind of a thing, like an IO operation. The RR register is 0, the PC is 3, the stack pointer is 4, and the instruction length is 3. This particular one is really nice because you don't have to decode the instruction in user mode to figure out how many bytes to advance the PC. This guy blocks, it gets strings like that, it pushes them up a channel to the thread figures out what to do. Okay, so, the nice little alt kind of channel, Plan 9 lib thread style loop. Once it's figured out what to do, it writes the command down the pipe and the VM can be resumed. What's the command look like? Dead simple. You write go, and then you give it a set of registers to modify. In this case, I've added 3 to the PC. How did I know how to add 3? I looked at the instruction length. Sorry, gotta love the Mac sometimes. I looked at this ILAN and added 3. If it was a kind of instruction that needed to be restarted, you wouldn't see that PC equals 6. This AX equal 42, I'm filling in a result register with the value of what I had to do. So that's it in a nutshell. The code's very small. It's very readable. Recommend taking a look. And that's all the stuff I just said, but it's text-oriented. I don't mean to be... I worry that somebody's going to say, I'm criticizing it. I'm not criticizing it, right? But, anytime you have a text interface, something like a VM, you are giving up a little bit of efficiency, right? So, but I like the design so much, it doesn't bother me. And unfortunately, I can't do the demo today because technical reasons, like our display won't work from my T420. But in the paper, I discussed how I can speed up console I/O by a factor of 700 by taking advantage of what you can do in Plan 9. All right, so the code, I have it on a repo in GitHub and at GitHub. And if you're interested, let me know, and I'll share it with you. It includes these slides and the paper. Implementing double pages, I changed main.c and memu.c and mem.h in PC64. To implement the shared thread VM guest address space and all that, I made some changes in VMX itself, the VMX command. Those are in some sense independent of the changes to libthread, but that lets me easily run guest VMs. And then extending libthread to include VM threads. I don't need all those files. It just was the first pass of just copying them in there and making sure this all worked. And then finally, the thing that's a little bit new, I implemented a device called hashz. And hashz is just one file, and it maps VM calls on, so a guest does a VM call, right? I'm sorry, a guest does IO in hashz, and that gets mapped to VM calls to the host. And so basically in hash Z, you kind of see your entire host file system. You actually see the namespace of the VMX command, but and that meant I got to remove every single driver save one in the guest kernel. And at the same time, things just got a bit faster because I'm not emulating a disk. I'm not emulating a Novell network device or something. So when the guest VM wants to open a socket, it just opens the TCP clone and goes to town. So that's kind of the power of sort of how this VMX works and the idea of VM threads and then what you can do in Plan 9 almost uniquely. So double H support. I added a VM proc argument. I got to see where I am time-wise. Sorry. Don't want to run over. And basically, I defined a thing called V bytes to page. And basically, when you allocate a page table page, it either allocates double pages or not. And I haven't added the thing to MMU put because it's kind of easy, and so I haven't worried about that yet. But I haven't completely implemented this idea that process memory is also the memory backing a VM. So VMs are still backed by dev segment. That's one of the next things I want to remove. And once I do that, there's a VMX kproc that I can actually remove. So I get into this in the paper, but remember I mentioned that VMs can address 0 and processes can't. But you kind of want to allow them to see the same memory. How I do that is, if you think about process virtual, it runs from 2 meg up to 16 meg in this example. And then 16 meg to 80 meg is the shared place. And 80 meg to 96 meg is that copy of low memory that the VM gets to see. So in dev segment, I have two segments, 0 to 64 meg and 64 meg to 80 meg. That's mapped to the VM with this being the low 16 meg and that being the shared place. So when I start a VM, I get a 16 meg segment. I copy this bit of it up there. That's what I get to the VM as its low memory. That means I can actually watch what the VM is doing. Right, could be useful to see if the VM is trying to corrupt its low memory, because it always does, especially if it's Linux. And then this shared stuff, I've got shared stuff. So things are possible that are kind of cool. Here's a host thread called the watcher. And the entire function of this host thread is to watch a value in the VM and wait for it to change. Right, this is that easy. It's just memory. So that's kind of nice to be able to do. Here's another guest thread that's very weird, but this is a thread running in ring 0 in the VM. There's no kernel in the VM, and it's calling functions in the host like pointers, right? And so, for example, I have a call, a VM call, and I pass the pointer to print because that's in my address space, and I get strings and away it goes, or I do a netcs lookup, right? And so in some sense, running a process in a guest VM and having it call things in libc directly is as easy as just running a thread. This is actually almost to the point where it's better than Acros, what we did in Acros. And in fact, you start to look at it and think starts to be almost like a super container, because like containers on Linux don't really contain. It's easy to break out of a Linux container. That's why a couple of companies that actually sold Linux container support as a product went out of business, right? So there was a company called Nitrous, and they started out saying, oh, we can contain a process, and it's so much faster than the VM, so we'll give you processes in a container. And about a month after I got my first account there, they said, oh, we're going to move everything into a VM now. It's so much more secure, which meant that, you know what it means. People were breaking out. The first Chrome OS support environment for running Android apps used containers, right? Not long after that, it used VMs. You can guess why. But in this case, it is in a VM. And yeah, you can do things there, but remember, it's the namespace of the process. So it's constrained in that way, right? We can use that namespace stuff to do some pretty cool stuff. So, but we can also now contain a kernel. And I mentioned we have VM call support. So here's the thing. You can't address the first 2 meg in a process on AMD 64. That gives me essentially 2 million parameters for RARG when I do a VM call. So I made it a little easy for myself. If the argument is less than 128, I just print the character. So this is the world's easiest console. You can move like, literal 0 to AX and do a VM call and it'll print it. This isn't actually the super fast console, but it's not bad. And it allowed me to write page table setup code and easily debug it in the guest. So because, printing things is easy. If I call with hex 1000, it dumps registers and TDEs, so I can kind of see how I'm doing. If I call it with 2000 to 2100, that's a system call. I had a lot of room, so I got sloppy with, my limits here. one FFF, you know, 1 and 5 Fs is like out, you're done. And then here's kind of the interesting one. If bit 63 is set, it means call a system call using the low 8 bits as a system call number. And finally, if it's greater than or equal to 2M, call a pointer. Right? So this means you're doing a function call. So you pop out of the VM to the host, and the host sees this. It says, oh, they're calling a function call with the arguments that are on the stack and in our arg. So this has turned out, again, this is actually a little better than what we did in Acros, and it's proved to be really nicely convenient. But you can go a little bit further, I realized. Now I can call from the kernel system calls. Or from the, I'm sorry, from the guest kernel, guest Plan 9 kernel, I can call system calls. So now all I need is a way to map I/O type things, like a Plan 9 device I/O type thing, to VM calls. And in the host, I will take those VM calls, which are system calls, and do them. So I wanted to show one example of that code, which is the VM call read. So the device is #z, it's named VM call. And when you do a read, I've attached an FD to the private structure, you know, that gets passed, the chan struct that gets passed into the read. And so from VM call function in this driver with the chan struct, if you've looked at this stuff, I grab an FD and then I call the host with this, I call VM call read. I have an FD, I have A, I have a long N, and, you know, the usual arguments, right? Now, one thing to note here, I use bounce buffer. It's actually not a bad idea. When Sean Florine and I measured all this almost 20 years ago, the IOs are not that big from processes in Plan 9. We measured like millions and millions of these things over a period of a day. The IOs typically aren't very big. Bounce buffer is not going to really hurt me a lot in performance, so didn't worry about it. The other thing to notice is the parameters. I don't pass the pointer to a struct, right? Because actually that's not very portable across all the guests and the hosts you might have. I pass an array of UV longs. So what I'm doing here, I allocate 8 UV longs to hold parameters for the read, okay? And then I've got a function called VM call args. Notice I allocated vec. I call VM call args. I'm going to fill it in. This is the system call p read. This is a pointer to an air stir. There's the size of the air stir. This is telling me how many args are this system call, and then there are the args, right? So I have a driver, a Plan 9 driver in the guest that's going to translate the driver opcodes to system calls, and then call that by exiting the VM call. So there's the VM call, and then, okay, here's another problem I hit immediately. I can't block on the read. So the first thing I hit is Acme wouldn't work, because Acme has a couple of reads in flight. So you can't block on a read because you'll block everything. You'll block the entire VM, actually. So I grab bit 62 to mean, you know, system call. Bit 63 to mean system call. Bit 62 is the system call is done. So I spin in the guest kernel on bit 62, and as long as it's not set, I call sked. And that's how I have the non-blocking read implemented. Funny thing here, blocking reads on directories are faster and don't seem to be a problem. So I may go back to blocking reads on directories, because to do the non-blocking read, I have to use an IOPROC, and IOPROCs are really slow. If you've ever used an IOPROC, their performance is really poor. We need a better mechanism than IOPROC to do, you know, asynchronous IO. They're just too slow. So this is a non-blocking read in a guest, waiting on bit 62 to be set. And then when it returns, it checks to see if the vector of 0 is -1, meaning an error, and it calls the error path, you know, as every other system call does. Otherwise, the return is that. We do the mem move from the bounce buffer, and then we're done. So I did that particular function just to show how you would do async. None of the other functions in #0 async hasn't been an issue. So once I need it, I'll do it, but haven't needed it. All right, here's the config file for a guest. I think the key thing to notice is all the IO devices are gone. Don't need them because #d provides my namespace, and namespaces in Plan 9 include your network stack, right? They include everything. So if you get the namespace right, you've got everything you need. Now that's really, really different than Linux, right? With Linux, you've got to have, I've got to have an emulated network, an emulated console, an emulated disk, and you can't get away from that. But everything in Plan 9, you open a file and do stuff, so it works. So the one thing that I haven't been able to completely kill is some of this stuff yet, because if you take that out, the kernel won't compile. I don't need them, but I can't compile without them because there are just some assumptions. And that's another thing I kind of like to fix. I'd like to be able to remove some of this stuff, and in particular, I'd really like to remove that, right? But if you don't include that, the kernel won't compile. I've got a much better UART. It's the UART VM I showed you. Put something in AL VM called done, but I can't quite yank that out, and I'd really like to yank that out. So, and the final thing is the boot RC. Oh, this is how you run it. Doesn't much matter, but notice my console is FD0 and FD1. Again, I can put a VM in a pipe, which is kind of cool. It's just a process, right? It just happens to be a VM. And here's my boot RC. I left this in because it's, I couldn't quite figure out why I'd want to remove it, so I left it in. And you can tell there's a little bit of hackery left in my, debug thing. Try and see if this works. But basically, I bind mount vmproc AMD64 over /AMD64 because mount vmproc is the #z, how it bound #z. And then I do a bunch of binds here because I'm binding the host namespace into my guest. And then I'm done. I run the RC and it works. So that's the RC, right? All that root is from stuff, and you don't need any of that, so I don't use it because I didn't care. Now, this is kind of an extreme case. Clearly, sometimes in the VM you want to test your device stuff, but a lot of times in the VM, here's something I'd really like to test. I want to test the NIC's multiple page sizes stuff. So NIC's, the basic page size was 2 meg, but actually NIC's also allowed you to have gig pages. If your heap grew to a gig, every page after that, when you did a break, you'd get a gig, and that was a gigabyte line page, and that was very efficient. But gotta work out how to make that come back to life again, and this would be a very convenient way to test stuff like that. Multiple page sizes. The other thing you can do, that double page thing I showed you, we could actually implement 64K page sizes in Plan 9 easily with that. And it's kind of understood at this point that 4K pages are just too small. 64K pages at this point, that seems to me like an optimal sweet spot. So 2 megs too big, like we did in next 64K, feels pretty good. So just something we can do. That is the talk because I can't do the demo, but during the hack sessions or later today, I can kind of show you how it works. And the last thing is, I need some help with this. Okay. I think there's a bug in my #z device, or there's some other bug that I don't understand going on. And what I was going to demo is I can start Rio in the guest, works fine. Sweep out 2 windows in the guest, works fine. Run Acme in 1 window in the guest, works fine. Okay, this is where it gets good. If I run clock in the other window, it takes over the entire display. So there's just something I'm doing wrong here. Or there's something that's just wrong that I've exposed. You never know anymore which. And I would, if anyone got interested enough to look at my code and say, here's what you've done wrong, that would be really nice. Or to see what to do to take this further, like I modified libthread. Should I have modified libthread or created libvthread and just say you've got to pull in libthread and libvthread? I don't know. So there's these structural things I'm not sure how to do. So, I kind of welcome anybody who would want to look at this and, make it better. And that's it. I think I'm on time. Yeah. So any questions or things I said that weren't clear? Yeah.
Yes. Please come through.
Oh, you have to talk to that.
We'll take the DNA sample later. Okay, so this is for, I guess, online attendees?
Yeah.
Okay, yeah, so my understanding is that you want to do this for performance, flexibility, and security reasons?
I don't know. I mean, primarily, actually, first is because I really didn't like the interface I had from all those VMs that used the device. And so this has turned out to be just such a convenient way to start a VM. Yeah. And you did get some performance because anytime you reduce the code surface of a VM monitor, you help security.
Right. So on the flexibility is clear to me. On the performance side, I'm just curious in general. What is on x86? what is the cost of a context switch from hypervisor to supervisor mode and from supervisor to user mode?
It depends on what year it is.
Okay, and on the security side, the fact that you can call host functions via a VM call, the way you showed it looks to me like the sort of the machine model and the attack surface to what is effectively the VMM.
Yeah,
it gets kind of porous, and it
and that's a really good question. And I didn't get into this, but the VM call support is defined by the process running the VM. And so basically, all those operations I showed, you can have some, none, or all of them. So I didn't get into the security because there wasn't time, but basically that thing where, call an arbitrary pointer, only if you want to allow that to happen. So that's an important question.
And I was going to say what would be what would you have to change in order to make the host that you're calling into, or the VMM that you're calling into, be another VM instead of the hypervisor user mode? Because then you could have a
I don't think it'd be hard, but you probably would still need to bounce to user mode enough to bounce back out to a SVM, but I'm not really sure. That's a really good question. I like it. Yeah.
It looks like something that would be pretty useful. I'm guessing that all the VM examples you had were tiny little snippets of code. If you were trying to run something larger that wasn't designed for running in this, like, for example, if I wanted to boot Windows in this, what would that take?
Actually, I think it works. So I actually don't care. so I have a certain bias here, which is I just don't care. But actually, the running of the guest is with a modified VMX, which still, you saw that URL 8250. That's there in part because the guest still wants to do it. So NBs, NAPs, all that stuff continue to work. It's just that I was trying to take this as far as I could with not requiring them. But that you could still really boot an unmodified Plan 9 that expected all that stuff to be there and it would work. And I think by extension, I don't think Linux would have a problem or Windows would have a problem. I would like to look someday at having Linux only use the namespace for everything it does. I don't think it'd be that, no, it'd be very hard, but it would still be fun to try and do it right. But no, I don't think this, well, QED, we did this at Google. I don't think this rules out running an unmodified guest. It's just that it allows some capabilities that you don't have any other way. So, yeah. Is there anything from the anyone online that's curious? Or?
Anthony is asking how stable is VMX. The menu says that VMX can and will crash your kernel.
Oh, anybody with any sense says that when they write one of these things. So I don't know. I mean, I actually looked at VMX and I think it's actually pretty solid. I think the thing that's super nice about it is it's tiny. And I think that always gives you, I mean, VMX itself is just so compact that I think that, you know, it would be open to someone auditing it and looking for problems and, you know, tightening it down. I will say that for a long time, hyperscalers did not want to run just the uncleaned up dev KVM in Linux because it was known to be pretty easy to break out of. So, you know, these things are hard to get right, and it's not like the non-VMX ones are really perfect. So, all right. Well, oh, you're holding us away from our.
Yeah. Internet question. Can I inject interrupts?
I haven't tried it. I don't see why not, because we did inject interrupts in the Acros stuff. But along the lines of inviting people to make this thing better, I'd be delighted if somebody wants to come in. And we did do it on Acros. We got as far with Acros as almost having the IMU working, and we did have direct device access in Acros. So all this stuff is sort of known to be possible, but I haven't really worked on that yet. You have to set up X2A pick That's one of the things.
And actually, a follow-up question for me, which is, could you make interrupts basically look kind of like a channel, a thread, thread channel?
That would be very nice. Yeah. Yeah. Building on the model. And by the way, what I mentioned, so pounds, I mentioned that 700. So pound Z, one of the things it does is internally it opens dev cons because your dev cons came from the host, right? And then that becomes your console, and all of a sudden you measure the throughput and realize that's 700 times faster than doing NB and outbeat to an emulated UART 8250, right? So there really are. So this is another one of these Plan 9 things. You can kill yourself in your UART emulation really good, or you can step back a little and say, what is it I was really trying to do? I was trying to do IO to a console. How can I best do that? And there are better ways to do it, like fit it into the Plan 9 device model. All of a sudden, you're running 700 times faster because when somebody gives you a kilobyte of junk to push out, that's a VM call. And in an emulated UART 8250, that is tens of thousands of VM exits for every, oh, I got to pull the bit to see if the UART's ready, right? Oh, is there an error? There are 2 bits you pull on that UART, right? And then, okay, now I'm going to push the data out. And then something on the other side is going to pretend it's a 50-year-old UART design, right? So you can do better if you sort of step back and we used to say this all the time with macros, and we learned it from Plan. And you get the abstractions right, then a lot of things just fall in your lap. So, anything else? All right. Well, thank you all.
Hello, I am Anthony. I poke at computers. This is a computer. Is anything happening? Like which way? Keep talking? All right, I'm talking. I like eggplant. Broccoli is good too. Are things continuing to happen?
Yeah, just keep talking.
All right. I have a presentation. It is.
Sounds good so far. If you start moving, the microphone could also move. And
Yeah.
that's where the practice comes from. Anyway, if you're not walking around as much as Ron, then it will be better. I'm sorry,
I will
Ron.
try to walk around. Wait, where'd the?
I blame myself.
Oh, there it is. I was like, there was a timer, and then I lost it. All right. You think we're ready?
Yeah, I guess this should be good enough. Anyway. So, yeah, as you can see, we just changed the schedule a little bit. So this is now Anthony talking about Nile.
Hi. I am Anthony. I am talking about Nile. Nile is a new Windows system for Plan 9. It is derived from Rio. The name is very clever. It's Nile is a river, Rio river. Yes. So when Rob Pike wrote about his Windows system history, he talks about Windows systems should be transparent. He's done several of these from the Blit through 8.5 to Rio. Each gets sort of a little bit more transparent. We have less windows, easier user interaction. So Nile makes a bunch of changes that are mostly aimed at continuing that line of increasing transparency, getting the Windows system more out of the way. So the first batch are sort of user interaction changes, the sort of how you physically manipulate the system. We simplify the mouse interaction. It eliminates all the menus or almost all the menus, depending on how you're using it. And we import Plan 9 from user space's scroll behavior. We make some look and feel changes, one of which is really good, and the other two are kind of mixed bags. One is actually kind of a net loss. We'll talk about that. And then there's two other sort of smaller changes that kind of go along with it. So the first thing we do is we get rid of the menus. The menus are the least transparent part of using Rio, not just because they're actually opaque, but they require you to stop thinking about what you're trying to do and think about operating the menu. Rio's menus have some really nice properties. They are local to where you're acting. They do the thing where it remembers what you selected last time, which is helpful for repetitive tasks. But even with well-designed menus, it's still something that takes you out of what you're thinking about doing otherwise. So it is at least an extra click and release. And between that click and release, there's also a observation and decision-making process in there, because you click, you see if you're on the right menu item and you release, or you click, you drag to the right menu item and you release. And then you do the action you're trying to do. You're diverting your attention, I just talked about, and it's easy to pick the wrong item. If you've used Rio lots, you've probably, delete and move are right next to each other. And it's easy to not notice that you've hit the wrong one and then the pre-select works really well for some things. It doesn't work as well for other things, and it inhibits muscle memory. So other kinds of like pie menus, one of the nice advantages of pie menus is it makes muscle memory a lot easier. Rio's menus don't really allow you to do that. But menus, aren't evil, right? Sometimes you have a lot of functionality your software wants to provide. Sometimes they're needed. Do we need them here? Spoiler, no. So Rio's button 2 menu has cut, paste, snarf, plumb, send, and scroll. Cut, paste, and snarf are already provided via the mouse courting, so we're just going to make those go away. We're just going to remove them. The mouse cording is really nice. It does really want you to have a 3-button mouse, but that's okay. Other window, I really like the fact that Rio, like Acme, embraces a particular actual hardware user interface and says, we're going to make the best user interface we can for a particular hardware configuration, rather than just saying we have a pointer in some sort of least common denominator sense. I think it really works well for that. This sort of emphasizes that just a little bit more. Plum and send are really important and frequently used. I use them all the time. I think that's probably true for most Rio users. So we're going to make them easier to use by taking them out of the menu and just putting them on the buttons directly. Button 2 will always send. Button 3 will plumb if you're in a text window. And we'll come back to scroll in a minute, but it's going away. So that's everything on button 2. Button 2 menu goes away, and instead we move send there. No, that's what I just said. Button 3 has new, resize, move, delete, and hide. This one's a little trickier, and there's a little bit of a cheat, but it's a cheat that works really well, I think. Resize and move are already available through the operations on the border. So we rely on that and remove them from the menu. Button 3 on the background is now how we create new windows, which makes it a lot more direct because you just click sweep release. There's no menu in the way when you want to do that. Which gives you faster window creation. So that's Rio's model for it, and this is Nile's model for it. You're just removing the first several steps there. Delete and hide, get helper programs. So there isn't a built-in way for Nile to delete or hide windows. This is the kind of a cheat. I mostly use delete and hide scripts that just writes the wcuttle message and deletes the window or hides the window. I put it in the tag of Acme, and it works great. Also, WinWatch can be used for this. You can delete things with WinWatch, hide windows with WinWatch. So there's really easy ways to do it, but it does sort of fall out of the window manager itself. So I like it. It is a little bit of a cheat. Hidden windows are another sort of tricky bit. This is the one place where there's sometimes a menu, depending on how you're invoking Nile. I always run it without menus, and I rely on WinWatch. I felt a little bad getting hidden windows require an external program. So there is a mode where you can put that back on the button 1 menu on the background. That's the only menu left in the system, and only if you really want it. So we move them off button 3 because the button 3 menu went away. Button 1 on the background, and option M disables this. I will, if you end up liking this and want to try it out, the version on the web right now has this backwards. I was supposed to be giving this talk tomorrow, and I was going to upload the fixed version tonight. So if you check tomorrow, it'll be like this. And again, WinWatch is obviously really helpful here. I should probably be the default, which is why I am making it the default. So we have the same mouse chords as Rio, the same window border operations as Rio, which lets us take those, that's a typo, which lets us take those functions off the menus. Button 1 on the background to see hidden windows. Button 2 always sends. Button 3 in a window plumbs. Button 3 on the background to sweep out a window. So what about scroll mode? That was the one thing we sort of set aside for a moment. I want to talk about Larry Tesler. Larry Tesler is most well known for being the guy who invented cut, copy, and paste, which is a pretty good legacy on its own. He did that as part of a much larger body of user interface research and design, and part of his big quest was eliminating modes in user interfaces. He did a whole series of user interface studies, first at Xerox PARC and then at Apple. And he found that entering commands in the wrong mode was the largest source of user error, and figuring out how to get out of a mode you were in was often the largest source of frustration for users. I think anyone who remembers their first time using VI can probably relate to this, but it shows up everywhere. So he spent a large portion of his career trying to eliminate modes from software. But they're not all equally bad. Part of his work was figuring out, okay, why does it cause these errors? Why do we have this frustration? And how can we improve that? He wanted to eliminate modes. He sort of softened on that position later in his career, but regardless, it's not always clear how to do that. So sometimes you're gonna have modes in your software. That's okay. What makes them better or worse? So Rio has two notable modes that it adds to the system. And I'm going to, my screenshots didn't work out, so I am going to, the first line here is hold mode. One of these windows is in hold mode, and one is not. Can you tell which one? This is in hold mode. It is easy to tell at a glance, and you also get the cursor inverts its colors. I just kicked out my power supply. Sorry, hold on. The user can tell quickly at a glance what mode they are in when they're working with things. This is really important for reducing user frustration and user errors. Hold mode, for people who aren't familiar with Rio, means things you type there don't get sent to the command that's running in that window until you take it out of hold mode. It's most commonly used for the mail program will put you in this so you can compose your message without getting parts of it sent a line at a time. But you can do it for whatever. So you need to know, is what you're typing being sent to the command that's running? So you have a really easy visual indicator. So that's good. The bottom one of those windows is in scroll mode and one is not. There is no visual indication. The only way you can tell is by going into the menu. Oops, wrong menu. The other menu, right? Sorry, I'm in QEMU instead of there. So it always takes me a second to remember, does the scroll here, that means I'm in no scroll mode, and I'm going to go into scroll mode. So not only is there no indication, if you're actually trying to find the indication, you have to remember that you're looking at the command to toggle it, not the current indication. So this is an example of how not to do modes in software. Because you don't know from looking at these what will happen if you run a command that's going to print out a bunch of stuff. So what about scroll mode? We're going to get rid of it. Plan 9 from user space did this 5 years ago or so, and it works really great. I really like it, so I brought it in here. The rule becomes, if you can see the bottom of the output and you have more output, it will scroll. You'll keep seeing the bottom of the output. And if you can't, it won't scroll. That's it. You now have a visual indicator of, well, there is no mode for the user to manage, and you get a predictable behavior based on what you're actually seeing on the screen. Oh, and if you want to change it, you just hit up arrow or page up or whatever you want, something that goes up, and you're not seeing the bottom anymore, so it stops scrolling. If it has a bunch of stuff and you want it to start scrolling, you hit end, and it starts scrolling. Oh, Larry Tesler this is more of an interesting historical note. So he did the first batch of this work at Xerox PARC while he was working on the Alto workstation, which seemed to inspire everything in the industry. Sun went off and created, the folks who became Sun created the Stanford University Network Terminal. After seeing a demo of that, Apple famously saw it in '79 and went off and created the Macintosh. Nicholas Wirth took a sabbatical, then took another one and created Oberon, which was the inspiration for Acme. And the Alto inspired the Perk terminal, which Rob saw a demo of, which inspired the Jerk terminal, and that line of succession, which was where all the ideas that we see today in Rio were sort of formalized along the way. So I think that's a nice historical tie-in. Transparent window creation and resizing. This is based on a patch from Andriy Merchovsky. So 8.5, the predecessor to Rio, when you create a new window or resize it, it only draws the border. Rio draws the whole thing, which looks slick when it works, but it doesn't always work. So if you have an accelerated graphics card on a PC and you're doing it locally, and your screen is not trying to push all that many pixels, it looks pretty good. If any of those things is not true, you get lots of janky, blocky redraws, especially if you're doing it over a network. I used to get very frustrated with it, where you try to drag out the window and it's lagging, and you're moving the mouse, and it feels very frustrating trying to get the position you actually want. So this goes back to the older behavior of the border outline. It's also more consistent because in Rio, if you use the menu items for new or resize, you get the drawing the whole window. But if you drag the borders, you get just the border redraw. So this way it's more consistent, which I think feels less surprising. Now we get into the dicier parts. Nile is darker than Rio. This is mostly because I work in my basement a lot and it's dimly lit. And having a very bright screen with high light contrast to the surrounding environment creates eye strain after a while. Also, honestly, when I was developing it, I needed a way to remember whether I was in Rio or Nile, so I just made the background darker on one. But the rest of this came from actually choosing to do that. It remains very comfortable in that space, but if you're in a brightly lit room or if you're outside, it is harder to read. So it's a mixed bag, but tells me, I think, emphasizes the point that it's not really realistic to say that one choice here is going to work for everyone in every case. There's also questions of accessibility and vision differences in people. This is just one example of that. Nile also makes the borders thinner. I did this initially because I was running it on a very small handheld device, and they just, with a low resolution screen, and it felt kind of just chunky. This experiment didn't really work out. It did feel a little bit better on that small device, but not much. And on the terminal that I used for a decade, it felt fine. And then I got a 5K display, and they're really tiny and hard to grab. And Nile makes border manipulations more important for resize, so it's even worse. So this was a loss. This part should go away. I'm going to revert this change. But it was a useful experiment, and we should report on our failures in science too. So the most novel thing about 8.5 in Rio, of course, is the file system. Nile keeps that and makes one addition, which is a per window font file. The way mostly this is handled today is you have the environment variable font, which is fine most of the time, but I don't know how common this is. I often have the experience of CPUing into a remote system, and now your font is set wrong because different portions of your lib profile set it differently. And when you run LC, all the columns are misaligned. So now we can tell what the actual in that particular window is, and MC can do the right thing, which just makes it look a lot nicer and easier to read. There's also a non-interactive mode, which was again for that little small handheld device. There's no access to the hidden windows. There are no borders. It just doesn't draw them. And all windows start up as a set size. And then you can use WinWatch to make it like a workspace switcher. It was nice on that small device, but I don't use it anymore. And I've kind of decided that that really belongs as a separate thing. So that'll happen at some point. That was based on a contribution from someone whose name I have forgotten briefly, but he's in the thanks at the end because I'm bad at mapping human names to handles. I need a Plan 9 from outer space code. So we are all interested in the future, for that is where you and I are going to spend the rest of our lives. So what's next? The next thing I want to do is make that font file writable, so you can change the font in the window. Nile, like Rio, uses libframe for actually drawing the windows, which is the same library that Acme uses, and Acme can do this. So I'm convinced I'm halfway through, but it doesn't work. So that's the next step. My main use case for this is often looking at log files that either have very wide lines, and I want to be able to fit them all, or I don't actually care about whether it's, I don't actually care about what it says. I just need to know if it's producing output. So I want that to be smaller and off to the side. So I want to be able to change fonts per window. I'm going to remove the non-interactive mode. There are a collection of theming patches. I was going to just use one of the existing ones, and then I read the paper on another Windows system that we're going to see tomorrow, and they talk about a way that they're doing it with the named images, which I thought was pretty cool. So I'm going to go evaluate that one. These conferences are great. And then look in Rio Windows. There's no way in Rio to search for the text. There's been a couple of patches to put look into Rio. I am sort of not super happy with the existing one, so I had started doing another one, and then I removed the menus, and I couldn't figure out where to put the functionality. So I'm going to get back to that. And relatedly, the Canon Cat had this leap. It had a dedicated key called leap on the keyboard, which was used for sort of incremental search as you type, which in other environments and I really like it. I don't immediately see how it would work here, but I want to try. Maybe that'll be something for next year. Oh, and so we use almost exactly the same file system as Rio. I have another unrelated Windows system that I'm working on that does the same thing. And then this non-interactive mode will probably also use the same thing. It seems a shame that that code is duplicated every time. And Rio already has it fairly nicely split. It's not entirely cleanly split, but it's pretty good. And I think it should be doable to turn that into a library. Different Windows systems can import to get changes like the font file, so you can get that in Rio and whatever else wants it. That is it. Thanks to Rob, obviously, for this whole line of stuff. The Rio code is really nice, and there's not much there for what it's doing. I would, if you are at all interested in these things, I would really encourage people to play with it. really easy to get significant changes from relatively little code change. Russ, the menuless stuff was inspired that a comment Russ made like 16 years ago. Well, I should say I've been using Nile for 11 years with just the menuless part, the menuless and the non-interactive parts. And then the rest got sort of added in over time. But yeah, I sent him a note as I was preparing to submit this paper saying, hey, I've been using this for a long time. I think it really worked out. Thanks for the thing. He said, I have no memory of writing that, but I'm glad you like it. So great. And the scrolling behavior is almost directly just a copy of what he did for Plan 9 port. Andrew Machovsky did the transparent resize. We miss him. And that's his name. Jesus Galan Lopez did the non-interactive mode. And thank you. The Nile is available there. This is another thing that I was supposed to do this tomorrow. So the presentation, because my brain is broken, this presentation is a C program that does the draw commands. And that will be, tomorrow, that will be at that URL. So.
Talk, thank you. Borders on Windows as manipulation handles. I mean, this is a mismatch we have all over all of our Plan 9 tools. As soon as you start using them on a high DPI display, we break, right? Because our mouse only moves as good as our arm, and I don't have a high DPI arm to use at the same time as my high DPI display. Have you thought of methods for fixing that rather than just making the things beefier?
Yes. And I haven't come up with any I like. There are. So first, we had a conversation, I don't know, a year ago about the fact that our acceleration is very naive. The mass acceleration in Plan 9 is very simplistic and could be a lot better without much change. But for that, what you really want is knowing where those borders are. And I haven't come up with a way to get the window manager to control the acceleration in a way that doesn't feel like more work than I want to do.
That's fair. The second one is, the scrolling behavior, the not having menus behavior, harkens back a lot to the Acme interaction, which is frankly what I mostly use as a window manager. And I'm wondering about the viability of having a tagline. It solves a lot of your, can you have a menu, can you have your external commands? What does that look like in Nile land?
I think that's a great idea. Russ mentioned it in that same post that he doesn't remember. Yeah, I think it's a really good idea. I would like to try it. I'm not committed to it because it is like pretty. Yeah. But I definitely think that's worth exploring. Yeah, thank you.
So, great talk, thanks, Anthony. I'm +1 with the single button experiment. The one thing I wanted to mention, the font, writable font file. The problem I could immediately see that most of the other apps would still be expecting and consulting the font environment variable, which is basically in the library in its desktop or in its Windows or something, right? So it's a library call which consults the environment variable. But we know that the Windows system forced the namespace and environment to run child programs. So do you think there is a workaround that, or you need to fix the library to consult the file instead of environment variable?
I don't think you do, actually. That's a good question. I think the behavior is right the way it is now. I think it's a small change to the semantics. Right now, the environment variable font is both providing instruction for what font to use and saying what font is being used. Nile separates those. So I think you keep the environment variable font for things to look at as a indicator of what font graphical applications should use when they come up, and you separate out what font is actually being displayed in this particular window. So if I start a Rio in a new window, I still want it to look at font because I don't want to mandate that it use whatever font that this window is already using for the text.
But isn't it's gonna create this dichotomy, like I declare that this is used, but the only thing is using that variable, that font is the Windows system itself, but not the program inside? I still like,
any program that's going to call initDraw is going to be setting up its own fonts. Like initDraw loads the font into the program. So the environment variable font is the instruction for the program saying what font do I want you to use. Saying what font the window before you run that is using is really a separate question. And there aren't actually that many things that care. In the standard distribution, it might actually just be MC. I have a couple other programs that use it, but I think in the standard distribution, it might just be MC. It's the only thing that actually cares.
Many years ago, one of my earliest posts to Nine fans was complaining that when I was too stoned, I couldn't pick up the 4-pixel borders. And that was in the 2000s when screens were only 1280, something like that. So, but what I discovered, it's hard-coded in Rio to 4 pixels, and if you change it and recompile, loads of other things break. So, goodness knows where it all is.
It's worse in Acme.
I just gave up. It was like, oh, this thing's simple, and I gave up. Or to change, and you're forced to use colours that the designer chooses. So that was another complaint of mine, that you couldn't change the back. Well, you can change the background, but there's no configuration. Which is, on the other hand, it's don't provide configuration because that's worse. But you want configuration for reasons sometimes that you say you like your a darker mode. I hate dark mode. Or when everything else is dark mode and one window is bright white, you want to be able to change it. So I would go for configuration, and I want big borders. I still want big borders now. Or the alternative is no borders and have the hot zones like you get in the corners because they're not used, and that would be very useful for resizing and moving. Not necessarily having to find a little magic area that you resize with. Magic areas. I was about to complain about magic areas after suggesting them, but Acme's changing the columns. You've got to hit. You've got to get the right bit. And same in other programs they use where there's not even a line drawn. You just got to know where the line is, and then be able to adjust it. I hate all that. So add the configuration.
Yeah, I mean, I'm sold on some sort of theming as an option. I think I've talked a lot about the importance of having sort of coherent, consistent choices, and I think he's right about all of that. But also, sometimes you're using it in an environment that wasn't anticipated, or you have visual or physical limitations that weren't anticipated. And to your other point about the borders, I mean, that's a real thing. The thing I've played with is being able to sort of click and grab the borders as you're moving, which helps with that a lot, but it causes other problems. It forces other choices that I wasn't happy with. So I don't know. I might look at that again at some point.
So my desktop terminal at home has this contour mouse, and it has 3 buttons, a scroll wheel, and 2 more buttons that I'm not using for anything. Would that be useful in this pursuit of eliminating all the menus?
Yeah, it becomes a question of, again, like Acme and Rio say you're going to have a 3-button mouse. we comfortable saying you're going to have a 5-button mouse, or you're going to have a scroll wheel, or like what choices are you going to make? I've thought about putting look on buttons 4 and 5 for forward and backward look, but I haven't gotten there yet. I think I like that because if you go back to a 3-button mouse, you're not losing anything that you have today, because look doesn't exist in the system today. I think that's a good way to think about using those additional things. But yeah, yeah.
Yeah, I mean, I get concerns looking at more mouse button things, because one of the hardest things when teaching people Acme is that there's no discoverability on the chording.
Yeah.
The chording is not something you discover, it's something you learn. You read the manual or someone shows you, and then you don't remember for a while, and then one day you're sitting on, you know, a laptop, and you've got your control buttons that are mapping to buttons somehow, and that's a whole different interaction you have to relearn, and I have to relearn it every 6 months or so when I forget to bring my mouse when I travel. And so please no more buttons.
Have you seen the mother of all demos, Doug Engelbart? Is that right? If you haven't seen this, go on YouTube for the mother of all demos. It is the mother of all demos. It's like the first demo of a mouse and video calling and all sorts of amazing stuff from, like, you know, like that should have existed. And his setup was he had, you know, standard screen and keyboard, and he had a mouse, and he had this weird 5-button chording thing dedicated just for chording on the left-hand side. And I've always kind of liked it, but it's not something people have. So.
Have you considered using pedals?
No, this is not Emacs.
I actually have.
Didn't make more use of pedals and user interfaces.
I have, but only as a joke. But I use a standing desk, and that would be really awkward to try to use. But when I bought this mouse at Goodwill, they had a set of pedals that were designed for a racing game, and I briefly considered doing that, but it was a lot of work for a joke.
About how fast you're running on your...
If you do the like walking treadmill thing, yeah. No.
I'm not sure if it's applicable, so.
For using more than one button or more than 3 mouse button, does I don't know the details, but does KB map work or no?
I think so. I haven't tried. I think it should. Or you have a like 5-7 button mouse, right? Yeah. Do you use KB map?
The defaults work for me. I haven't seen
Yeah, I know. I've used the defaults with it, but I'm not sure if KB map works. I think it should. Yeah.
So you have a file to control the font. What about having a file to control the border width as well?
Well, the border width is a little trickier because of how it's defined with other applications that run in it have to be aware of the border width in sort of unfortunate ways. There's no theoretical reason why that couldn't work, but it would be, you need to create some new mechanism for applications running in it to know what their sort of safe area is for them to do what they want in.
Or maybe just change it so that the border is drawn outside the area.
I tried that. You run into other problems with you can easily make it so that you can't grab your windows anymore, and it changes how the sizes are calculated.
in it anyway. I was thinking like you need a hot zone which is wider than the border because you're having a hard time selecting the border.
Well,
So-
that's another thing, making the hot zone separate from the visual border. There's no reason those have to be the same. That someone again, I'm terrible at mapping humans to like IRC handles. Someone in IRC, someone in IRC suggested that. Was that you?
I don't remember.
No, someone in IRC suggested that, and I looked at it briefly, but haven't had time to poke at it. I think it should be okay.
The answer just is actually nest two windows. Right? One window is your and there's a window inside of your content, and you have the content off of the inside.
I have a solution for this in Lola. I will talk about it tomorrow.
Oh, excellent. Excellent. Oh, you're the person. Excellent. Now I know. Yeah, I'm going to steal your that background, that named image thing. That's great. And maybe other things. Yeah, yeah.
Okay, hi. I have a question about user cognitive load and those things. So I'm fascinated by Plan 9, although I'm sad to say I've never actually used it myself. So I'm going to ask a heretical question. So I appreciate the work of Larry Tesler and Engelbart and so on, but I do wonder how maybe Tesla didn't, or in his environment, he didn't assume multitasking or event-driven OS response to the extent that we do. So you could argue that modeless is just I am typing in my editor while being on a phone call, and someone is seeing me on their screen because I have a video camera. And some of these applications I'm interacting through I have my keyboard peripheral or my camera peripheral and so on. So some of them are more modeless and some of them are less. So in the environment, in the computing environment that we find ourselves now, why is arbitrarily positioned overlapping windows important? And that's the first thing. And the second thing is, why not use the keyboard instead of the mouse to the greatest extent possible? Because it seems to me that while I understand that it might be easier for the user to discover a modeless user interface initially. And of course the argument is that if you are using a tool for longer than just right now, you can you become one with the machine, and you can move faster with your keyboard. So why arbitrarily positioned overlapping windows, and why use mouse instead of keyboard?
Yeah.
Thank you.
Well, I think there's actually those are both good questions, and I think there was actually a question 0 before that about the. I think it relates to what Paul said about the fact that courting is not discoverable, right? So this model sort of assumes that people are going to learn in a way that's different than like the Mac style interface, where it is intended to be more discoverable. And I think that relates to the question of the mouse and keyboard. At least, well, I'll take them in order. Why overlapping windows? I think that's a really good question. When I'm on Unix systems, I use a tiling window manager. I'm not religious about the idea that arbitrarily positioned overlapping windows have to always be the right answer. I think they have lots of benefits. I think tiling window systems are nice too in other ways. So I don't know. I think they can both exist. I think they are separate things. And why the mouse versus the keyboard? I think it is harder to design a keyboard interface for stuff like this that doesn't rely heavily on modes in ways that are confusing to users more and have a higher learning curve than the mouse. I think the keyboard focus tends to come from a place of focusing on a perception of efficiency because your hands are on the keyboard. There's been a bunch of studies that argue, some more convincingly than others, that what you're perceiving as more efficient isn't actually the same thing as what actually takes you longer. I don't know. I like the mouse. If you want keyboards, like that's cool too. All right, I am like 30 seconds out of time, so thanks.
Hey, anyone watching us live now? We will be back in a few minutes. Some people are still returning back from lunch, which was quite nice. And yeah, sorry for the delay. And yeah, Paul wishes you were all here. So does everyone else. And I guess you haven't really seen it. Every speaker gets a beautiful 3D Glenda here. Look at that. So if you come to the workshop yourselves, you may get one of those. All you need to do is submit a talk, get it accepted, and come here.
One, two, three. 1, 2, 3. 1, 2, 3. 1, 2, 3. 3, 2, 1. 1, 2, 3. 3, 2, 1. thank the Plan 9 Foundation for the opportunity to talk about a project of mine, 12D, which started out as an artifact when studying the RFC literature on the foundations of the web. An artistic study, one might call it. And then this artifact fused with my study of the Unix and Plan 9 literature, where 12D transcended its initial narrow technical scope and incorporated broader system design ideas. 12D is still work in progress, and in the next quarter of an hour, I will give a brief overview of how reading the Plan 9 papers inspired the design of my web server I use since a few years to host my little zoo of web presences. D, written here in IPA, from French La Toile and Unixese D, is a web router for both net/HTTP server that multiplexes multiple domains and subdomains over a single static IP, designed on top of one hierarchical namespace with a host names as directories approach. I've just now tried to describe 12D in a single sentence, though it might not be too illustrative. This shouldn't come as much of a surprise as 12D's ultimate goal is to mellow the historically grown technical boundaries of the web and render itself invisible. A usage example might be more illustrative than me blabbering on about the features and properties of something that aims to reduce. For this example, the DNS configuration looks like this. And in particular, you have a DNS wildcard pointing to one IP, and this IP address is connected to a singular virtual private server with root access. Now, on a local machine, I will show a shell transcript of me configuring a local web page topology and then pushing the entire web page topology defined on the local file system all the way through to the web server, and then it coming out on the web intact. So I start off by initializing a Git repository because I will be using Git as a file transfer mechanism. And so Git links the local OS file system to the network layer, and then on the server side, the Git construct is reinterpreted as a virtual file system and then served. To construct the local web page topology, I create in this Git directory an HTTPS directory to indicate the scheme, and then an a.jfrecht.com directory where I put in an index file, which I intend to serve. And then in the same Git repository, I create another directory now with a different subdomain. And in this different subdomain directory, I create a subdirectory, and in this subdirectory, I create an index.html symlink. And I've just put the real path invocation here, so you can see I haven't swapped the ln-s arguments. So you have a file which symbolically links relatively and exceeds the boundary defined by this p.jfrecht.com directory. So it goes out of the directory namespace and then back into the other domain, and 12D correctly translates the symlink to a redirect and correctly arranges for the TLS to be configured for both subdomains. Okay, now this is all simply done on the local file system, and now I push it up. So I create an empty commit to instruct Git to bundle to create a Git tree, and then I bundle everything in the Git repository into a Git bundle and pipe this through SSH to land on the server as a file. And then now I have this bundle, and now I'll show the server side how it unwraps this bundle. Okay. Now, okay. This is still a local example to show that it worked. So I need to restart the web server, so it detects the newly created bundle. And now I use curl to test my web server if it functions correctly. And what you see is curl by default only tries a port 80 HTTP connection, so quality correctly upgrades this initial request. And if you request for TLS, it truly has an HTTP layer redirect. This redirect, then if you invoke curl with the link following flag, correctly serves the content of the initial index.html under the a.jfrecht.com file. So in sum, operations I did on my local OS file system were fully translated to the web. Okay, how does this look server side? As mentioned, 12dx acts atop a singular virtual file system, which may be assembled by a single function such as fsys right here. And then I use a companion library to act on these virtual file systems as values. So multi-IFS takes multiple file systems and squashes their directories to appear as one file system to be served to 12d. And so you could imagine that you insert multiple virtual file systems for multiple sources and assemble this huge file system which represents all subdomains and domains to be given to 12d. And in this example, because I used this bundled Git repository, I use another project of mine called Egual, which is a full implementation of Git in Go to support this, or to attach to a file system encoded in a Git bundle. So a Git bundle is a PEG file with some references, and this creates an index and creates virtual files which lazily unpack into this PEG file. So you have you get some laziness. You have these constructed file systems which then truly represent your web page topology without too much overhead. And this width size is just a small adapter to let 12d know how big the size is, because for a PEG file you need to, or for bundle file you need to know the end to know where the trailer started. It isn't self-describing. And I talked a bit, I said that I use a companion library, and this isn't too integral to what 12d does, but it is required and it's not present in the standard library. So I need something to create this multi-FS to create a file system from various file systems, and then because I have this HTTPS/domain prefix, I also need a way to indent. So if you have a classical single domain web page, you can just indent it with the domain you want, or you attach it to, and then push it into multi-FS. You can also go from a function to an FS and convert a singular file to a singleton file system. And then this last definition, this FS handler, is an escape hatch to be able to construct more dynamic web pages inside the file system interface. So this is one feature of Go that you can unerase interface receivers. And now this is the main body where you attach your file system, give it to 12D. So we are now server-side in the main function of the server. I then agree to the terms and services of Let's Encrypt, and crucially, I pass the capability to the certbot or Let's Encrypt subsystem to disable port 80, because as you saw earlier, an HTTP request is upgraded to HTTPS, but certbot spins up a server on port 80 to do the certificate authority management. And so you need to temporarily shut down this HTTP upgrade and then re-enable it. And because I don't want spurious requests thrashing my Let's Encrypt limit, so I need to whitelist the domains I truly want to offer up. And for this, I already use the file system interface to read the directory HTTPS to get the names of the domains I want to truly serve up. And then finally, I call listen and serve. And this is then the entire web server. So in a few dozen lines, I have served directly from the local OS file system a multi-domain web page topology over TLS 1.3 and HTTP 2 with automatic certificate renewal. I want to now cite two papers as inspiration for this work. The first is Mr. Pike and Mr. Peter Weinberger's Unix paper from '85, The Hideous Name, in which they, as their introductory example, use an email address, the hideous name, as non-homogeneously accrued various routing descriptions. And incidentally, the @ in this email address is a part of the non-homogeneous name, which gets smoothed into a string of bank-separated Unix mail path components. And so then they talk about the concatenability of sending mails to certain agents and then further and then further on, and how this composes neatly. This is not unlike I translate the URL / after the domain or after the host name. In my case, these are both slashes, but they mean different, or they are of different semantics, into the homogeneous namespace of Go's virtual file system, which is fully / separated. And the other paper is from 2000, and this is Rob Pike's lexical file names in Plan 9 not getting the dot right. And this paper strongly argues for this global homogeneous file system naming scheme. And to give a bit of context, because nowadays you often interact with the lexicality in file names, but what he argues against is individual files claiming they know their name, but inadvertently polluting the namespace with their own context as different referring sources see the same file claimed name for certain operations like directory traversal. And in the context of Plan 9, embed your file, or if you embed your file systems in different contexts, this pollutes the system beyond usability. It is in part due to how these ideas about namespaces proved themselves on Plan 9, which led to their codification as the io/fs.fs interface in Go in 2020. This is the design draft. And the interface landed in Go 1.16, released not a year later in February of 2021. I think the reason I developed 12D is that it brings me a bit closer to having a system with Plan 9's ideas. Network-enabled transparency across machines and implementation details culminating in one cohesive system. Instead of 9P and IL, I use io/fs.fs and Git. And most crucially, the bravery to stick to not bulk on extra features, but to stick to one interface was learned from Plan 9. Thank you.
Why did you choose Git? Why not tar or?
Why did I choose Git as a file transfer mechanism? You can use tar, you can simply embed it in tar. Or tar is maybe a zip file because tar does discovery. But I chose Git because, first of all, I am in an environment where I'm comfortable with it. I'm writing this Git implementation. So I partly used the bundle because I just had managed to really crack a bundle. But also or web pages with small edits, I really benefit from the Git mechanism I don't need to type an entire bundle through SSH. I can simply push then read. I wanted to show the bundle because it shows the versatility of these virtual file systems.
So in practice, your website is served off the Git rather than off the static bundle.
The question is if my website is served from a Git repository to which I push. But as I've talked about in the paper, I'm not currently using it for my webpage, but I plan to. This is also, you can have a bare Git repository and then live attach over the network to this bare Git repository on a different server and then funnel everything through. But I haven't yet tested if the latency is acceptable. I'm talking things 1 to 3,
Okay.
3 to 1. All right.
All right. So yeah, up next on Flash.
All right. So hello. My name is Arkadiusz Kozdra, and I will tell you some things about my project I started recently, which is called uGlendix. You might have heard of Glendix, which was rather a Plan 9 / Linux distribution, which was supposed to execute unmodified Plan 9 binaries on Linux, but I decided to use user mode features of Linux, which is why there is U before Glendix. My main problems with Plan 9 were that it mostly lacks broad hardware support. Even 9 front, which aims to be more hardware compatible at a broader scale, does not support some features. For example, in my laptop, Wi-Fi does not work and the touchpad does not work because someone decided to connect it via SM bus, which is I2C basically, and not use USB as everyone does in every sensible laptop. And typical Linux user space is too complex. So I decided I would try to make a hybrid. As I discovered that there is a feature called syscall user dispatch, which is pretty much an option that allows to capture a system call event in user space without having to write kernel patches. So someone did write Glendix, but it was Linux 2.6 times, so quite a while ago, and the patches are very outdated. So yeah, I decided I would make it in user space because that would allow to have even Docker containers with Plan 9 binaries inside, and it would be just great. Apparently, someone already did that effort, and even two separate people, and did it and called it 9, which is just a clever wordplay because it connects wine and 9. And someone else did, and it was called 9aout, where a.out is the executable format used prevalently on Plan 9. And those two implementations are okay-ish. They can run binaries like cat, echo, and maybe some other things, but they cannot run ls, for example, because they don't implement read or they don't implement wstat, which is why chmod is impossible. Not to mention mounts or architecture portability. So yeah, a side note is that syscall user dispatch is also used by Darling, which is a Darwin emulator for macOS binaries, and there are no other projects, and especially Wine, which was supposed to be main consumer of the interface, does not use it yet. I searched GitHub and all the other big forges for syscall user dispatch, and nothing showed up except those 4 projects. My inspiration chain was that I've written it from scratch and focused on entirely user space implementation so that it does not bit rot with kernel upgrades, and to reuse as much of the system layer as possible. So no FD wrapping, because we know how this is painful in APE, for example, the NC POSIX emulation environment on Plan 9, or dynamically rewriting paths, because it's against the spirit of namespace being just any namespace and configurable and everything. I decided to write Linux style C because I can't 9 yet. Sorry for that, but I hope your eyes don't hurt reading my code. Then I tried simple programs like echo and cat, and they worked, so that's great. I tried more complex programs like ls. I've written the reader and all the other necessary parts. Then I tried some more complex programs like 6C, which is a C compiler for AMD, RC and MK. Then I discovered that U9FS and DROTM have some similar concepts, because U9FS is the program that runs on Unix systems and serves 9p. It's like export FS but on Unix. And it has some overlap in scope with my project, namely converting Plan 9 API calls, maybe not system calls, but accesses, to actual Unix syscalls, like, for example, the wstat. They made some decisions because wstat is supposed to be atomic, but that's not possible on Linux because you cannot express the operation of simultaneous rename, truncate, chmod, and whatever else in a single system call. So it's not possible, but they chose some opinionated way to make those operations as close to atomic as possible and reversible. So I used just that implementation from U9FS, and I also got inspired by some things that are done by DROTM, which also does some similar things. Then I found out about 9aout and borrowed some ideas to set up syscall user dispatch correctly. And then I ported to ARM, implementing syscall user dispatch for QEMU, by the way, so that I can develop on my phone as well as my laptop, because my phone has an ARM user space. And then I ported the thing to seccomp for all kernels, which is not as flexible as syscall user dispatch, and seccomp filters cannot be uninstalled once installed. So I just chose to trap the first page of text and hope that nothing Linux sits below the certain position and nothing Plan 9 sits above the certain position. Then I added /srv, and it could not be implemented in 9p because the 9p the protocol, because it cannot distinguish clients. Fortunately, Fuse does distinguish clients,
it supplies the process ID in requests. So I used a fuse-based helper. For those interested, SRV works, the SRVFS works like you create a file in SRV, then you write a number, and the file descriptor that's referred by the number is installed as a file in SRV until you close that file you just opened. So you can post a pipe in SRV, like both one of your file descriptors and allow any other process to just grab it. And I used also a recent kernel feature for that, which is called procfd openfd. Fortunately for me, it was there. And I also added /net, which was extracted from Drotem and VNC server. Some benchmarks I did. They are not performance benchmarks per se, but these show what is Uglendix useful for. I can rebuild 9 front on it, all architectures, by running mk install in syssource. And my paper itself was typeset inside Uglendix on 9 front. And I also can mount and manipulate file servers like .srv and 9660 srv. And I can only do and I can also do simple HTTP 1.0 requests. Why 1.0? I will talk about it in a moment. The main problem with it is that v9fs in Linux is buggy, extremely buggy, and I was not prepared to have it so buggy. So let's move to the hacks I needed to make. First one, I did no special handling of /env. It's just a boring normal directory, and it surprisingly works for even rebuilding the 9 front distribution, which is great. I implemented no logs, no rendezvous, which is apparently not so important in these cases. No GUI, which might as well just work, except for the v9fs bugs I mentioned. With imported devdraw, because I did not hack together any devdraw for Uglendix for demonstration. I need to try it but I have no idea how. Maybe Drotem can be used for that, or something smaller. Nothing is 100% feature complete because I chose the approach that compatibility is vertical. So apps that work, or applications, not necessarily programs, but tasks that work, tasks that can be performed. For example, rebuilding the distribution. This is one task, it works, so I'm happy. And I did not focus on horizontal compatibility, like correctly implementing open syscall with every possible edge case. Because I thought this is boring and in the long term pointless, because even the original implementation can be a bit different than the spec, right? I found some problems along the way. For example, you cannot manipulate your namespace in Linux just like this. To develop this thing, I used unshare-nr, which creates a new namespace and mount namespace. And you can mount things inside it, but you cannot mount v9fs. Those who remember from last year, maybe, know that the kernel says v9fs verboten. So I just touched my kernel, which is dangerous. If you like to escalate from the patch, I can tell you that it's possible, but I did not write any proof of concept because it's just a work in progress patch, so that I can develop it without running it root. I also have some bonus patches for Fuse and v9fs, which allow transparent read syscall on directory FDs, because when you call syscall read on a directory FD file descriptor under Linux, you typically get error, and the error code is this file descriptor is the directory. You cannot just read it. You need to use get dns64 or some other directory specific syscall. I added a very simple patch that allows to transparently translate read calls to underlying read calls on Fuse and v9fs, which just forwards them as a read message underneath, because it's rejected by the kernel before forwarding, and now the implementation can reject it. All right, and the things I found. Yeah, I know I should share my patches. I will hopefully do that in the coming month for some things at least. I found out that netfs implementation, which is the common denominator of v9fs, NFS, the Sun one, I don't remember the name. Yeah, all the network file systems, which are supposed to be network native, and the Microsoft one, CIFS. They return, for example, if a write syscall is, if the remote end returns an error in response to write request, the syscall returns ulong max, signed long max, for no reason. I made a patch for that. It might be possible to exploit that, probably, but yeah, that's just one problem. Another problem is that v9fs is overeager, unable to return short reads. It tries very hard to read on. If you try to read 8 bytes and the backend returns just 4 bytes, it does not return from the syscall, which is I cannot comprehend that. Why just not return to the user what you got? But it tries to read the next 4 bytes, and you cannot prevent that. I disabled caching, I disabled everything, but it still keeps trying to read the remaining 4 bytes, even if it's not there yet. And another problem, which is related, it calls writes. So when you issue a short write, it does not send it immediately. It just tries to... I don't even know what it tries to achieve. Sorry for bashing v9fs. It's really a great implementation of 9p, but these problems prevent any use which is not related to plain files. Any file that has special meaning is just inaccessible over v9fs because of these problems. Another thing I found is WebFS has inconsistent error string. Some operations just return an error string from the underlying op, and some try to invent status codes. Sorry for being too long, but this is my last but one slide. There was no syscall user dispatching. I wrote it. There is an initialized variable in mk main, which is probably room for further development of 5e, detecting uninitialized stack variables. And another thing I tried to do, finally, is plan9 port bootstrap. That I ran Ubendix with a hybrid of plan9 port and native plan9 inside Ubendix, and tried to bootstrap compilers from themselves. They are apparently not so portable because they use some features that are not standard C. For example, here it declares a struct after declaring it inside the struct, which is not visible, and it is a mismatch. For example, here there is a field name conflict because ELF32 header and ELF64 header have the same names of fields, and it's a conflict in GCC. Yeah, and ideas for future improvement: improve networking to run a CPU server and connect back from a draw term, like I said before. Bootstrapping 9 from plan9 port, as I said before. It almost works, but 6L does not reach a fixed point, which is a bug, or maybe something more fishy. Hybrid ProcFS, maybe that would be useful. Improving FSRV, because it currently only allows posting file descriptors. It does not even allow listing the directory. Parallel builds, which is improving /env beyond just being a simple file system. Simple GUI integration, maybe. And a final general thought is that drawterm emulates the kernel, and it tries very hard to emulate everything at once in one binary. And this is, in my opinion, a violation of single responsibility principle. Why there is no /net app which just emulates /net on Linux? Just mount /net and use it as /net on plan9. Why there is no /devdraw plus mouse plus keyboard for app for XO Wayland? Why is there no separate audio app which just mounts the dev audio thing and uses a respective backend? I think this is a problem, and this is something that is missing in the ecosystem, and I hope someone can maybe do something about it. Maybe me, maybe someone other. Okay, and this is all I have. Do you have any questions?
Some feedback from the internet. The internet says, kocham cię. That means, I love you.
Thank you.
Quick question. So, from your description, it's not really clear how much of your work took in kernel and how much in user space. So it seems like you touched kernel a little, but otherwise most of the work went in user space, and this the true abbreviation you kept mentioning.
Cisco user dispatch.
Yeah, that.
Okay, the changes I made in the kernel are entirely optional. They are only for returning unmodified information from the root syscall, because it is translated twice from 9p into Linux syscall, into Linux directory format, and then passed back as a directory and converted back to 9p. So it's inefficient and it loses information. For example, usernames, group names, and things like this. But directly passing it provides keeps the information intact. So it's just an improvement, but it's yeah, and the other patches are also like this, just optional.
A question, more of a comment. If you take a look at muck on 9 front now, the bug that you complained about is fixed.
Thanks. Okay, thank you.
We get another very short question from the internet. Is the math.h the header file about fmol, that function?
Which one? Fmol?
There was a math.h file.
Yeah, math.h conflict. Right. There are. Yeah, I also encountered it, but yeah, this is the thing. There was log2, I believe, and some other name, log2, and I have it in the repo. Sorry for no live demo, but okay, I can run. It works, right? And MK, it also works.
So if you're building the Plan 9 toolchain using the Plan 9 tools through Uglendix, why do you care about the systems math library?
I tried to do the bootstrap with GCC and using Plan 9 port headers. So it's just a conflict during bootstrap. So math H, log2 and round. And I think fmol is also a problem, but it's somewhere else, not in the compilers. Yeah, this is too hacky, the bootstrap process. Yeah. Yeah, but I can do a quick live demo. I can mount a DOS partition, just like I would do on Plan 9. Yeah. And I can create the debugs are from the binary, which can be just compiled out, I think. But yeah, it works.
yeah, you know, whoever knows Nix, it's been revived.
So calling it revived is an interesting statement. So my name is Paul Lalonde, and I'm one of 3 people working on it. Ron was kind of the impetus to get this thing moving again, and Thierry has been providing some work on the legacy version. I'll speak a bit more about the versions that we end up with this as we go forward. The cast of thousands, of course, is all of the nice folks at Nile who've made a system that I can build and work in, and has been working as my daily Plan 9 driver now for probably about 6 months. Very pleased with where that's gone, and many thanks for that support. So CPUs, when Plan 9 was invented, they were already many core. There was sometimes 2 and sometimes 4, sometimes SMT. We have very different choices to make today when we look at high-end machines. There's a machine from Esperanto with over 1,000 RISC-V cores with SIMD units attached. This is probably a bad way to run Plan 9, running that on M4. So, we have very old historic assumptions about how time sharing should work that are based on the idea that many people, many users are on the machine, and that we want to bill them, so we want to track how much work they're doing on each of the cores. We're time slicing the work and carefully counting how many cycles they use and how much memory they use. We haven't done this in years. But the accounting principles are actually still kind of there in how people think about time sharing. And what you wind up with in those kinds of situations is an OS that's actually in the business of perturbing your processes. You might want a process that executes nicely and uniformly and holds its resources well, but you won't get that. The system will perturb what you're doing if you have multiple processes running. There's housekeeping, there's instruction, there's interrupt delivery, there's other processes. And on the many core machines, your processes get moved around cores. I'll go into a little bit why that might be a bad thing. And it can happen at all sorts of times. It can happen because you hit your time slice. It can happen because you made a syscall, and suddenly you're going to come back and probably be another core. There is some stuff in Plan 9 for pinning a process to a particular core. And that just makes the scheduling a little worse for you on the whole in most cases, if you're having to share with other applications. So the typical choice, right, is to say we're going to serve the OS work to a process. We want to bill the OS work to a process, and that means that we want that process to be the only thing that suffers from its system work. So if I go off and make a system call to dev random, and it wants to compute right there. So, right there. So. So the observation from Nix is to say, hey, we have so many cores. Why are we taking all of that hit when we can just leave that on some trash core that does this work? And typically, when you're making a system call, you're not going to work. System call takes some resources, except maybe just burning some of your time. But burning your time and perturbing your resources just seems like a bad trade-off anymore. So instead, we move the OS tasks to what I like to call a trash core. I don't think the Nix folks actually used that word originally. I think TC, trash core, time sharing core. And we'll accept that that the application core will be idle during this time. That's actually one of the kind of the fundamentals of that shift, saying it's okay for this thing to be idle while it's being served, and when it comes back, you'll be perturbed to continue. So Nix. I'm not going to give a full overview of everything that Nix does. But there's a bunch of things that we didn't re-implement while doing this work. One of it is that we have the application core where we're going to run this unperturbed environment. We have this time sharing core, which does all of. You see, I didn't say trash everywhere. Okay. We have this time sharing core that does all of the other service, does the housekeeping, services all the interrupts,
might be some large number of these time-sharing cores. What we didn't implement was a kernel core whose only job is to do the services from the kernel, or an exclusive core, which I don't even remember what it did. You remember, Ron? Or Thierry? Okay, so you serve your kernel directly on there, so you don't get the advantage kernel. So that doesn't give you the benefits of being unperturbed by the OS, but you know that the OS is committed to you on that core. So I'm not sure of their utility as is. Actually, I have to say some words by the time I get to the end about how sure I am about the utility of NIX, because we need to measure it. But we'll get there. This is why it's a work in progress. So comes the question then of, how do you actually do this? The NIX code base, as we started, was a dead code base that Thierry has had some luck in reviving on Legacy. But the code base itself isn't very compatible with 9front, is one way to put it. And so this was grabbing a pile of that implementation, pulling it over to 9front, and fitting it into that same space. And if we think of what we're trying to do, effectively, all of our bring up on the machine starts with every core bringing up the same function, the same main that it gets jumped to. That's the lovely thing we call Squid Boy for no reason I understand. I guess I understand that much. I don't see the connection or the relevance, but that's okay.
There isn't one.
Perfect.
There is.
There is? History, please.
It's a German thing.
Oh, so he can't tell us.
No, that's right. But there is a line somewhere, maybe in a fortunes file, that relates back to this and why he chose that.
Okay. So we will have to.
Don't take your octopus out to sea or something like that.
Okay, we will have to search the fortune file until we find the reason that the boot code is called Squid Boy. And there's a pretty simple change that we make to Squid Boy at this point, where every core starts running this. We do one quick grubbing through some configuration files to say, or grubbing through the configuration to say, is there a NIX AC line set? And that lists all of the cores that should be ACs. This is a candidate for a user interface improvement, but as is, it's just a comma-separated list of cores. You have to be aware when you're setting this right now, and this is a to-do space, of whether any of those cores are SMT, and so running back to back if you wanted to share them or not share them. You have to leave some open for the OS to use. So core 0 is always not an XAC, but other than that, you could overwhelm your machine by being silly. So handle with care. But then after that, the dispatch changes almost trivially between the two sides. If it's identified as an AC, then we go to our AC versions of these functions and init, and then go to the scheduler for the AC, which I think I describe in more detail in the next slide. And otherwise, you just go on and run your regular Unix kernel or Plan 9 kernel. So the interesting thing is that the NIX kernel that runs on the AC does effectively. It has a different. Do I have this on the next slide before I talk through it? No, I don't. I lost a slide days ago. I haven't rewritten it. So this is awkward. But what you wind up with is that it handles only the traps that must be handled on that core. And I think that's 4 of them. Not even page faults are handled on that core. A page fault is forwarded to the time-sharing core and runs there. Double faults, machine checks, things that you don't think of as service, but are effectively critical and take down your machine when you hit them. Those wind up running in that, get trapped in that loop. Everything else is forwarded back to the time-sharing core to function. The trap handlers are all replaced with a whole new set of trap handlers that do almost nothing, that just do this forwarding task. And you know, you can see the lovely that it is. We just have a pile of new trap handlers that go to the forwarding code, except for the fourth matter. So that's the principal form of the change to the code. The other one is now, how do you actually send your process over to be running on that core? And this is a place where maybe those people in the room who worked on Nix can educate me a bit. Nix had two ways to launch a thread, or to launch a new process to an AC. One was to call sysexec as a new system call that would do exec, only send it to an AC to start. And the other one was actually running through rfork. And I suspect that that's a side effect of history of writing the code and figuring out how the pieces work. Yes, we're looking at you.
rfork was the one that was kept after. I think the exec was old.
Well, that might have been the original. Damn if I remember.
I know that you were adamant into making XAC.
Okay.
Yeah.
I think it's the easiest way to start.
I was adamant, I'm sure for good reason. I don't know.
Okay, so
I think it had to do with paging in and the interaction with paging in the things, and I can't remember.
yes, sysexec gives you a place to do the pre-paging if you need pre-paging.
For HPC reasons, yeah, okay. So startup time is super critical in HPC. We don't want to be bouncing back and forth between an AC and TC and page folding and everything, because if you look at the default path, you set up all these mappings, and the first thing you do when you start a program is page fold in the first page of the program.
Okay, so.
And so exec AC, the whole point was pre-page everything because it's HPC and you don't want to waste time on page folds.
Okay, so for those following online who probably didn't hear Ron's answer, exec AC in an HPC context, exec AC lets you start up much faster because you're not page faulting in the first pages. You can pre-page the world. You can pre-start everything and then go. Whereas if you're outside of a critical startup performance space, rfork is nice because an AC is just a system resource. So you want to be able to attach the system resource to whatever program you're currently running or to the program that you're starting by saying, hey, put this on core. And that's a very clean interface. But as always, there are performance trade-offs to clean interfaces. So if we wind up using this in HPC, we'll have to think about that startup cost. I'm not going to torture people by walking quickly through the code of run a core, but the principal thing is that when you want to run something off to an AC, the AC is sitting if it's idle, it's sitting in a loop. That loop is querying for new work coming in just a little buffer. When work arrives at that buffer, it kicks it off. It's just a function pointer. It will run there. Otherwise, when you want to run it from the TC, say, hey, move this process over there, SCED catches that case. You've flagged it to say, go to the AC. SCED catches that case, essentially queues that work request, that function pointer, sends it off to the AC, and hangs there waiting for either a trap, a syscall, or a return from that function. I guess the return is strictly speaking a syscall, and takes that return from the syscall as its cue to do something, to handle the trap, to handle the syscall. The other thing that comes back, though, every time you come back from the trap, is a continuation. So you've got a function pointer that says, hey, here's where I want to continue. And that's what you then send back after you've filled the trap and goes on. It's a really small mechanism. And if anyone wants to read it later, maybe on Saturday morning, I'd be happy to walk through it in detail. So, I said a little bit about sysexec AC, a little bit of a rump that we don't know if we need it. As soon as you're using the sysexec AC, there's a bunch of goop that's living in the system for replacing the system call vectors that I think we don't need to do anymore if we don't use the sysexec AC version of the world. And we can maybe hack through that on Saturday and try to understand if we rip it out or if we make it cleaner. There's also a per AC, when you transfer control back and forth between the AC and the TC, there's some TLB flushes and shifts that happen in there. And I'm not convinced that we've got them right. In particular, really only would need the TLB flush on the AC if you were going to a different process, because you want to kill that, keep the processes isolated. But otherwise, you absolutely don't want to have shot down your TLBs in that transfer. That's untested right now, and I'm up for ideas on how to test it properly to not wind up with bad code where we want good code. So I said a little bit about this earlier. We really have two versions of this coding right now. Thierry has been keeping, working up the 9 legacy version, and that's got a lot of pieces that are lacking in what's in 9 front right now. Maybe that's in my next piece of work. And then the 9 front version that Ron and I have been working on. And it's currently living in a GitHub page that Ron is hosting. You could point to my version too, but Ron's might be more reliable. They're identical. Well, yeah, because you started. He who goes first gets it in the GitHub tag. And so you're welcome to pull from there. We try to crack the front of 9 front and stay compatible with it. We haven't had to make a lot of changes, but it's just making sure that we're integrating and still functioning. We need to go to a CI model, and yeah, that's not at our top of priorities yet because there's only like 2 of us grubbing around in there. But we really do need a continuous integration model in there. So there's a few things that aren't done because, again, work in progress, and we've spent tens of hours working on this already. You can go to an AC. You might be able to come back. But right now, the only way I know to come back from the AC is to end the process. In particular, if I go and dig in the rfork code, the branch for RF cancel core is commented out because I was crashing. There's some questions about some of the error handling in the kernel and expectations in the error stack that were being problematic there. One of the pieces that Nix did that was very interesting and is useful for writing real programs is that you need to be able to communicate between ACs, and you need to be able to communicate fast. You don't want to do communication by shipping stuff down a pipe through the operating system and so on. You want to be able to drop your things in a buffer and have the others consume it. And ideally, you don't want to spin weight on that. You want to, use monitor M weight to maybe get woken up when the data is ready instead of just continually hitting memory, burning your bus. So those primitives need to arrive. We need to figure out whether to just port them in or whether they need to be rewritten and so on. We've talked about rfork and sysexec. I need an expert in interrupt routing in 9 front to talk with me. I haven't found one. No idea if anybody knows how our interrupts are delivered. I think the by default round robins them, and then we would catch them and we would send them off to the other core. That would perturb the AC. If someone knows that at all, I'd love to talk with you and figure out how to fix it so my ACs don't get perturbed. And all of this leads to the critical thing. We haven't measured this, and I really want to measure this sometime soon because I want to know that there is an advantage to running this way and to having these changes to the code rather than just letting it run raw. It may be sufficient actually just to kill IPIs and enough performance. Who knows? So I want to measure that. It's going to be a while, I suspect, till we get the other issues sorted. But then the question is, what do you use this for? What kind of applications? I mean, I used to work on a GPU that was 32x86 cores sitting on a ring bus with some texture samplers. think it'd be pretty cool to be able to build something like a GPU implementation in software on this kind of architecture in our space, saying, these cores are doing these kinds of vertex operations, these cores are doing the binning operations, and these cores are doing some rasterization and so on. And I think we have a path to do something really quite simple for that communication and set up on here, compared to the hoops we had to jump through to make it performant at all on x86 on top of FreeBSD. So I'm very much looking forward to trying this. Yeah, there's the code. And I think that's the end of what I had to say. Happy to take some questions.
You know where the microphone is? Perfect.
Hello?
Given the need for the AC to route kernel, like to forward or delegate kernel calls to TCs, how does it choose which TC it wants to forward the system call to?
Currently, given the need to forward to TCs, how does the AC choose which TC to forward to? Currently, it doesn't have any such mechanism. So you have effectively a little rump of a process that's running on the TC, or that's running generally in the thread pool, and when that one gets scheduled, you will get wherever it's running, it will go. I don't think there's a priority mechanism on it.
It's a little more complicated than that. So if you look at SCED, there's this step in SCED, which we can't bring the code up, but it's going to make a decision about, what am I going to do? Am I going to go to 2-user? Am I going to be tracing? What am I going to be doing? And we added an element to that case called 2AC. What happens is you tell the AC to go do what it's going to do, and then you wait. And now essentially you're in this. You're waiting, and eventually, you get run again periodically, and you say, "Is that AC still busy? All right, I'll just hang out again."
So it's like a dedicated thread, essentially.
Yeah, but it's not blocking the machine because the scheduler is running. So, blah blah blah. All it really means is you don't have to make that decision because the scheduler is going to schedule you onto the available processor when you come back. If you've been wired to a core before you start all this, then you'll resume on that core.
So the actual sort of semantics of this looks very much like making a GPU call.
Yeah.
Yeah, it does.
Yeah.
It's sort of before GPUs were hot.
And much simpler than calling it.
And actually, at the time we did this, IBM and Intel were both telling us you're going to have a sea of CPUs, because then all of a sudden GPUs happen and nobody's saying that anymore. So the world rotated. All right. There, right there.
Yeah. So this is what I mean by a little rump of a process running. The process is there; it still exists, but it's not the process that's now off on the other side.
It's the whole heavyweight process. It's just that.
It's.
If you look at run a core,
Mm-hmm.
in run a core, you actually.
This code is on the TC though,
No,
right?
that's the TC. Yeah, you're right.
And so
That's the TC code, and now we're going to go look. See how run a core is in TC, and then if you look at run a core, there's a thing down there. Yeah. Yeah. So the trick here is to realize that run AC returns because the AC is going to run. Then you set your proc priority normal, and then you kind of sit there and hang out and wait for the TC to tell you, wait for the AC to say, "Hey, I'm actually done," and so you're in that never-ending for loop there, right? And you inside of the kernel and the TC, yeah. So I had actually remember all this when I looked at it again because I couldn't remember how the hell we did this, but then it slowly came back.
So you're not quite always in that loop, right? You're actually spinning in run AC for it to return. Then you fall into this on the first return, and then at the bottom you call run AC again to where is it when you return from this call.
That may be right, but Can you show up a little?
Yes.
Yeah, you're right.
Yeah, so
Whoops.
that's okay.
Yeah, I said it
Yeah,
was
there it
wrong.
is. Yeah, so in the bottom of that loop, you go back to run AC, running the continuation and continuing that process. Yeah.
The funny part about this is if you squint and you look at this looks like exactly what you do when you're running a VM. So, and you can even think about saying, wow, if I could run a VM on a dedicated core, as you know, that's what cloud providers call bare metal. What they mean is bare metal, but in a VM. Actually, that's not even true anymore. They're finally just actually offering real bare metal. But for a while, certain companies that you and I worked for, when they said bare metal, they really meant, well, actually,
If
you're
you
in a
don't
VM.
give me a VMC, I don't have bare metal.
Exactly, That's fair.
I have the whole discussion of XAZ and everything, so maybe we can go.
Good. That would be good.
Awesome. All right, thank you very much. Oh, another question. Somebody has.
You saying you had the receipt?
There's no button.
Just a precision. There is one version on 9 legacy and the other version on 9 front. This is not a fork. They are not already a fork or mix. It is simply because I have neither the knowledge nor the technical abilities of Ron and Paul, so I'm back, and I wanted to have, let's say, a stereo vision of a thing, trying both on 9 front and 9 legacy, in order, when there are problems, to be able to have two views of a problem. Because there can be things that are more correctly done on 9 front and things that are more correctly done with 9 legacy. So this is not a fork. I will continue to follow and try to, well, I'm not quite sure I will make for the gap between Ron and Paul and me, but I will continue to try to keep pace with their development, and this is not a fork. And this is a proof too that someone like me can help. They have done developers' work. I have done only programmers' work. This was it worked on 9 legacy almost immediately. I've done very little thing with it. So there is some room for anybody wanting to learn slightly.
And I did bring a development system to work on this on Saturday. I've got my little 12-core Intel jobby that I've been using for development that we can trash and retrash and trash again and keep going until we have results that we like. So, okay, thank you.
right, so our host, Edouard, is going to talk about, I don't know what actually.
WebAssembly.
Right. Oh, yeah. Beautiful. To hell with it.
Yeah. Nice. So, first of all, I'm very happy to be here again. I really like this conference. It's very nice, and I learn a lot every time I come. So I'm going to talk about WebAssembly and Inferno. I know some of you wrote like the system, but some of you also came because you are curious about what Plan9 is. So Inferno is basically so the history will be talked about, but people who have lived through it. So I'm not going to talk about the history of Inferno. But the way I see Inferno is a lightweight Plan9 that can run as an application on Linux. Basically, I will show you in a few minutes. So you don't need to run a VM, you don't need to install 9 front, which I've never managed to do. So you just run a small Linux program and you get a full-fledged operating system using the principle of Plan9. So it's very nice. On Inferno, they call 9p Styx, which is the river that runs through hell, according to Dante. But the river you must cross when you die is actually called Acheron, and this is the name of the program. Actually, the resolution is not good, so I need to change the size of the window. Anyway, let's try again. Yeah, so Acheron is the name of the WebAssembly runtime I've been building, because it allows languages to cross into Inferno and be run in Inferno. And yeah, that's it. Let's go. I'm gonna first explain what exactly is this runtime, what WebAssembly is and what runtime does. Then why would I do that? And then I will show you the code, how it works and how it's implemented. And lastly, I will see what next steps I will take, and maybe we can take together if you're interested in that. As for the what, so basically WebAssembly, I assume you know, but I will still explain. WebAssembly is it was born for performance reasons. So basically, the web initially was to share documents. So you had a nice document, and you could link other documents, and everything was nice, and everything was fine, and it was working very well. And then, like in like one afternoon, they added the language to browsers, and now you didn't have just a document that you could parse. You had a running application, and if you know any mathematics, you know about Rice theorem, and you know that a document is a finite thing that you know you can parse and display because it's like finite and nice, and you can follow the path. But if you have a running program, maybe you have an infinite loop in it, maybe it's a malicious program, you have no guarantee whatsoever on the behavior of the program. So we went from a platform for documents to a platform for running like arbitrary application. And the complexity step is like huge, and you have absolutely no guarantee on the memory it will take, on the actual behavior of the program, or whatever. So security-wise, it's a disaster. And nowadays, like a normal browsing day for anybody is downloading hundreds of megabytes of untrusted program and running them on your machine. So in order to do that securely with huge quotes, you need to do that in a walled garden. Like the browser has become the ubiquitous platform, the platform that runs everywhere. So if you want to write once and run everywhere, you will have to write JavaScript or whatever. And because performance of JavaScript is not good, or was not good, what they did at Mozilla, for example, was take, in JavaScript, let me show you, in fact, what we can do with JavaScript. I always like this part of the demo. So let's just take some JavaScript, and if I do like, I don't know if you can see. Let's try that. If I do 1 plus 1, I get. The answer is already, but you know. But if I do like 1 plus 1, oh, it's the same. There was a way to have like 11, and it's 11 and 2, and you had like typecasting. If you switched, it was something else. So minus, yeah, maybe I think it should work.
Try object plus object, like empty object.
And then?
Empty object.
Yeah, no. So this is technically right, but my point is typing on the fly is very expensive to do in perspective. So Mozilla was like, yeah, if we don't do that, and if we don't do garbage collection, maybe we can be faster. And they called that async.js at the time, and it was a way to like be faster. And they took like LLVM intermediate representation and compiled that to this subset of JavaScript, and it worked quite well. And after some back and forth between Google and their V8 engine and Mozilla, they were able to like stabilize this into a kind of bytecode, which is WebAssembly. So basically, it's a way to compile stuff to be run on this ubiquitous universal platform that the browser has become, and not pay too much of a performance tax. But the browser itself is like, when I think about it, I'm a bit mad, because it's like the perfect walled garden, but for privacy, like for security reasons. For example, you want privacy from the website. You don't want the website to spy on you. But if you think about it, like Mozilla is almost dead, and the only browser provider is Apple a bit and Google. But Google is the guy spying on you and is selling you the walled garden. And the biblical metaphor is not that bad. Like, the guy who built the garden didn't give you clothes, so you are naked in the garden, and he can look at you without any, you know. And inside this garden, there is this big tree, and if you ever eat one piece of this tree, like if you try to access the file system, then you are cast out of the garden. So the metaphor actually works quite well. So what I want to do is like WebAssembly. So I want to implement WASI, which is like hey, WebAssembly is nice, but you cannot have any of the old operating system primitives that we expect, especially files. So what we're going to do is normalize on a way to call some functions that will let us access files. And so you can run WebAssembly outside of a browser in another runtime, and you can access files from there like a normal program would. And so this is a way to escape the walled garden, but like being all together in this new world and agreeing on how to access. Basically doing a parallel like garden, but a bit one. So this is what WebAssembly is, and what I'm trying to do is implement this on Inferno, because Inferno should have been like what the browser is now. Like, if instead of a browser we had Inferno, we could have namespacing. So basically any thread, any adversarial program could run in a very tightly contained environment without affecting too much of your system. And what I would like to do is to mix and match. For example, I can go to an application as a service accounting program. Like, I can log in into my accounting program to make sure my accountant can file my taxes. And I can connect to my bank account. But I cannot do both at the same time. Whereas with Inferno, I could like mount my bank and mount my accountant, and I could run both at the same time. So my accounting program can call the API from my bank if they have one. But what I would like to do is on my own machine, with my own data, be able to like mount pieces of all the services I'm using and run them at the same time in a way that I want. And with Inferno, it's easier to do that, whereas with the web, it's basically impossible. So like Inferno would be a better web browser than the web browsers, and I would like to see this vision happen. And also, I like Inferno, I like to play with it, but Limbo is nice, but not very easy to write program in if you want to just do something dirty and quick. Therefore, having a WebAssembly runtime will allow us to actually use not Limbo programs. And also, I'm teaching using Inferno, but my students, they don't speak Limbo, so they cannot write programs in Limbo, and I have to use, let's say, creative methods to embark them on the boats to cross the Acheron. So basically, I give them a bad guide in Inferno. Let's do a demonstration. Let me just put it. Let's try that here. Yep. So this is Inferno running, and it's going to be. So Acheron is like the name of the library. So the program to run the program is Acheron. So be prepared because it's very quick. Are you ready? 1, 2, 3. Ta-da! Thank let's go back to, maybe I can. Yeah, I'm gonna. So what we just ran was, so let's see. Yeah. No, this is what we run. This is this is a textual version of the actual binary, and this is like the basic hello world in WebAssembly. So what you do is you say, oh, I can put maybe a bigger font. So what you do is, from WASI, import the ability to write stuff, like the write system call that you all know. And it's a function that takes like 4 integers and returns 1 integer. And you declare 1 page of memory, and in index 0 of this memory, you put your string that you want to print. And it's only 20 minutes, so I'm not going to detail what the API looks like, but it's full of indirection. Basically, what you're giving the fdwrite function is the place to look inside the memory for the address inside the memory where your string you want to print is. So there are a double layer of indirection. I'm not going to go into that. I can explain it to you on Saturday if you want. But basically, this is like the most basic way you can use WASI compliant way to write your stuff. Keep that in mind, because in a few minutes I'm going to show you how all this WASI stuff is actually implemented in Limbo. That's it. So this is an hello world in WebAssembly. I have also coded an hello world in C, and I've used LLVM to compile this to WebAssembly. Let me show you. So just before I do that, so 16 lines, okay? Keep that in mind, 16. This is the version compiled from LLVM. Oh, okay, let's go to the end of the file. Ready? 1600 lines. So just to be frank, this is not working yet because there are a lot of instructions in there that I haven't implemented yet. I will, but and this is C, it's nice. If you use Go, you get basically the whole Go runtime in WebAssembly. So just running hello world compiled from Go would be a huge step up. I'm gonna do it soon, but it's not done yet. Anyway, let's try to get back on track. So this was the demo, yeah. So how does it work? First, don't read everything. What I wanted to show is, the gray stuff is, these are the parsing the WebAssembly binary. So the gray stuff is what you are supposed to construct from the WebAssembly binary, but the WebAssembly binary, in order to be small, because remember, WebAssembly, its goal is to be given over the wire to multiple clients. So every byte you can shave off is, like, monetary speaking, a lot of money saved for Google or big web actors. So you have a lot of indirection because if you can save off 1 byte, you will. So for example, you will, if you want to know the type of a function, so you define a function internally. The functions are stored and referenced by their index, but the imported function go first, and then the function you are defining inside your module go afterwards. So your function number n, which is your first internal function, goes after the n-1 imported functions. And if you want to know the type of this function, you need to look into this array. This array will give you a number, and this number is actually the index in the type array. So function n, you look at index 0 of the function array, and this will give you another index that you need to look up into the type array in order to know the type of function n. So it's not that complicated, but when you are deep in the code, you don't understand anything. So I did this in order to see what I was doing, and once you have this like printed, it's easier to follow. Yeah, that's it. And we can sit with this and discuss on Saturday if you want. So let's look at the code now. Something I would advise you to do when you are writing a program is not only to write a README, but also a manifest file. A manifest file is like a manifest for a cargo ship or whatever. You just write down whatever is in your project, and this allows me to quickly guide newcomers to what is it. So, for example, I used Yak, of course, to write the parser, because Yak is available on Inferno. And those are the constants that are defined by the norm. But I'm kind of mad at the people who normalize the stuff, because
they had 256 numbers to choose from, and they managed to do collisions. Like the magic number for the type section is the same magic number as for the table, whatever. You see what I mean? It was not necessary. They don't have 256 value yet, so they could have made it so it was. And this complicates the parsing quite a lot. If I go back to the manifest, so let's see the grammar first. So this is the grammar, and so basically your binary is divided into sections. So you have a magic number identifying the section you are in, and then you have the content of your section, and so on. And most often than not, your section is a bunch of stuff. And you want to know when you are done parsing the stuff. And if the magic codes were unique, I could just know that I've overstepped the current section and know in the new one. But because they are not, I cannot do that. And so most of the token I get cannot be recognized just from the data. They need some context. And as you know, YAC is for context-free grammars, but this is not context-free at all. So the parser has some state, and sometimes I need to tell the parser what's coming up so that it can recognize the correct token. So it's a bit of it's not that complicated, but still, it's kind of back and forth between the parser and the grammar. And this is what the parser looks like. So, for example, I have to tell the parser the size of whatever section it is I'm parsing, so that when the size is done, the parser can output a back-end token that I need to know that I'm done, which is not an actual token in the binary. It's just a virtual token that doesn't actually exist in the binary, but tell the grammar that I'm done and I can switch to another state and so on. So it's a bit technical, I'm sorry, but the idea is to show that it works, but because the format is so optimized for size and network, it's less optimized for ease of interpretation. What next? Something I want to do is let's try again. Okay. Sorry, let's go by end. Sorry. Okay. This is basically where the actual executing happens. So we have a program counter, and we go through all the instructions one by one, and we have a big switch statement. And once we find our instruction, we actually have some classical limbo code. So for example, this is the add instruction. So we just pop two values from the stack, add them together, and push the result back. So, and this is the same for all instructions. This is naive. It works, but it's performance-wise horrible. So what I would like to do instead is translate those WebAssembly instructions into this. This is the virtual machine that makes Inferno run. I would like to translate this into these instructions and be able to use like a native Inferno facilities in order to run that. I think it's possible. I have no idea how, and I would like to work on that. Last thing I wanted to show was how it's implemented for external functions. So basically, I have defined a module with an init function that takes a lot of whatever, and then the memory. The memory is like the memory of your program. So every external function is given the whole memory of your program, and every external function must conform to this type, which is like take an array of value, return an array of value. So it's very vague, And if you want to implement a WASI function, you will leverage the fact that Limbo is a dynamic language that you can load at runtime. So the way it works is when you load a native function, it's this thing. Basically, you load this module, like a compiled Limbo binary, and they are all have the same interface. And when your runtime wants to call it, you just call this Limbo function. And the effect this has is WASI is not like a set implementation of Acheron. You can basically switch WASI implementation, and it looks like this. So, for example, the write function is implemented as a Limbo module, and it's basically just a wrapper for a where is it? syswrite, which is the write function for Inferno. But if you had Inferno in an embedded system and you wanted to write on the serial port, you would just switch out this write to write to dev whatever, and you would be writing on the serial port without having to recompile after run. That's it, and I'm almost done. Sorry, I'm rushing through it. Yeah, so next, I would like to actually run the hello.c. That would be nice. I would like to implement the full of WASI, which will let me interact with files, which will then let me interact with the whole of Inferno, because Inferno is basically files, like 9. And that will open the way for DevDraw and actually implement graphics. And someday maybe run Doom on Inferno in a few years. We'll see. That's it. Sorry, I'm a bit late.
I don't know if it's still available, but have you tried it on the Internet Explorer ActiveX version of Inferno?
I should. Okay, you can go for CKL. But Pete has done some work getting something workable with browsers and Inferno. I should talk to him about that.
So I saw that you have this YAC parser of the binary file, as I understand it.
Yeah.
Why do you need a parser in the first place? Because I also started implementing WebAssembly once on Plan 9 though, and I just read the binary file and parsed it like the way that it's explained in the document. You don't really need anything like YAC. You just hand code it. I mean, it's a bit annoying, but I bet yours is also very annoying. So this is kind of one part of what made me give up on the project. Or maybe I haven't given up, I don't know yet. But it's certainly what made me stop, because it's just tables and tables, and as you say. But that would be my suggestion or my question, like why YAC, and maybe you don't need it?
It's basically like the default choice, and I didn't realize when I started that it would be so complex. A bad technical choice, but I'm so much in now that I could change. That parsing is not the hard part. Like maybe articulating everything is afterwards, and I want to play with the optimization part. So maybe we could rewrite the parser. It's not that there is a parser that works as you say, and maybe we could just copy it, and it would be done quite well. Yeah. Thank you then.
now, apologies for this. I had this all set up nicely so it would just work.
That was your first mistake.
Okay, so what was it? What was the font name? I want to use that one. Why is this not working? There we go. Oh, wait. And I want to actually write the font command. Why is my... Okay, there we go. Okay, there we go. Apologies for that. Okay, so basically, the talk I'm going to give is going to be a very quick summary of what PKI is, or at least web PKI, how Plan 9 handles it today, or doesn't, and what we do about it, assuming we decide to do something about it. So I'm going to just kind of try to rush through this because the timer is ticking. So the very short summary is of what PKI is. It's basically the thing that gives you the little green lock on the corner of your browser. Sometimes that lock might even mean something. So what does it actually give you? It handles two things. It handles encryption and authentication. Encryption is basically how you get a channel where no one else can listen. And authentication is how you know that you're talking to the right person. And for a secure system, you actually do need both. You can't just have encryption. If you only have encryption, well, you have a very, very secure connection with the person that's stealing all your money at the by pretending to be your bank. If you only have authentication, the person that happens to be listening in can take a look and say, "Oh, those were your credentials. I can pretend to be whoever. I can pretend to be you and steal your money by talking to the bank and pretending to be you." So to get a secure connection, you need to encrypt the channel, and then you need to authenticate both sides of it. And what public key infrastructure does is it tries to handle both of those use cases. So the way that you these are all the things that you'll end up hearing about and all the buzzwords that are involved in this. So the way that way that PKI tries to handle this is through having a cert authority. So it's not a great way of handling it, but it's the thing that we chose. The short summary of how this works is there's a certification authority that says, "Oh, I know who everyone is. And therefore, I can issue you a certificate that says who you are, and anyone else can, because they know who I am, they know I issued that certificate. I can trust that certificate that says that you are who you are." So examples of these might be VeriSign, Let's Encrypt, etc., etc. Let's Encrypt is especially interesting because because it's free, but also if you happen to have a domain and you can host something on it, that's good enough to say who you are. And as we know, there is no way that anyone would let someone host a file on a computer that they don't own. So this is completely guaranteed to work 100% of the time. Anyway, it's what we have, and it's better than nothing. The way I think about it is that Let's Encrypt is a great way to prevent, say, your ISP from injecting ads into the sites as you browse for a couple of extra bucks. And then we use it for everything. A while ago, we actually implemented an Acme client for Let's Encrypt and all the other Acme providers on 9 front. So we ship with something to support this out of the box. You can just grab certificates as you want. That's not what this talk's about. Anyway, so we have all of these certificate authorities, and the way that we know that these are the authorities is that these authorities, basically, a system like Linux or Firefox or other operating systems like Chrome may decide to ship with a set of certificates that they know as the roots of trust. So they will have, technically, Let's Encrypt isn't one of the roots, but they issue, I don't remember who issues their certificates that they use on your certificates. Sorry? Okay, ISRG. Anyway, so the ISRG is one of the roots of trust, and there are probably about 50 others, like the Chinese government, that we all trust. And these all end up being shipped with your browser. So what we do to verify them is we will basically... Yes? No? Did you switch my fucking internet again? Yes. There's a phone over there. Could someone just move it in between the two computers? Yeah. Yep. Just put it somewhere on the desk and between the two. It is tethering. Yeah, just put it somewhere there. Yeah. And hopefully things will just come back if I manage to find it. It does have the tethering on. Yes. I thought this would work better. Actually, could someone just unplug that laptop and bring it over? You would think that Wi-Fi would go more than like 20 feet. Okay.
Do you need the power for that?
No, it'll be fine. It's got something like 6 hours, 8 hours. Yes, no. God damn it. Great. I'll leave that in the background there and hope that this works while I just open another. Nope. Okay. Oh. Oh. Where? Oh. Got it. Ah. Okay. Okay. So, as I was saying, so what the client does if you're trying to run through yes, as you can tell, this is what I'm thinking about. As the client, as I was saying, as the web server serves the certificate, the client has to verify it. And what it does there is it has to maintain it has to have its trust store. And as a client, you have to maintain it. So if 9front goes this way, we would have to ship a set of certificates that we keep up to date with the OS. They don't rotate very often, but we'd still have to do it. And then whenever we connect to a website over TLS, it sends us its certificates and all of the intermediate signing certs. So, you know, orb.dev was signed by Let's Encrypt, which was signed by ISRG, and so on. And as it goes, and then, so we have to verify that that certificate chain is valid, and that everyone that's signed is the chain is actually someone that's supposed to be able to sign the chain. And then we have to go and verify the names, which means that, you know, if I'm trying to connect to orb.dev, my personal website, and it comes back and says, oh yeah, this is the certificate for badguy.com. Well, maybe I don't want to connect to badguy.com. Or maybe I do. It sounds like it would be a site that sells some pretty cool stuff. But I have to verify the name. And how are these certs done and how do I do it? It's a fucking disaster. I don't know how else to put it. I think I was being kind there. Yes, but this was a particularly talented committee. So X509 is an extremely complicated way of encoding certificates that doesn't actually have all the information you need. So what happens when you try to, so a certificate signer is uniquely identified by the public key that was used to sign a certificate. And therefore, of course, the certificate doesn't include the public key of the signer. Does not include the public key. So what you have to do to find out who signed a certificate is you take a look through your certificate store and say, oh, this guy's name kind of seems to match. This guy's name kind of seems to match. This guy's name kind of seems to match. Let's see which one of them actually has a valid certificate or has a valid signature. So you just try them all. And if you're lucky, one of them will match. I believe when I looked at the implementation that Go uses, they stop after about 250,000 failures and give up and say, that's probably not going to match. I could be wrong. It could have been only 25,000, but it was 25 with several zeros. The other thing that's kind of nice about this name is that it's actually not a single string. It's a sequence of strings, and each string contains its own encoding, so it's theoretically not even a sequence of strings that are encoded in the same format. Though I believe that the spec says that if they have different formats, you're not supposed to accept it. Which means that, of course, I'm sure that someone out there issues them in a different format and you have to go, oh, the spec says this, but the real world, I don't know yet. I haven't gotten that far. Anyway, that's the mess. And I just went through this, so sorry I spoke ahead of the slide. Anyway, that rant. Pretend I said it again. So how do we handle it today? I think that kind of sums up how Plan 9 handles it poorly. What we do right now is we have a set of thumbnail or thumbprint files in syslib TLS, which is basically a set of hashes of the public key. So we strip out a whole bunch of the non-cryptographic garbage from the cert and hash whatever is left. We put that into a file in syslib thumbs, and then programs that decide to care, which isn't very many of them, go, okay, so let me open up a thumb file for what I want to do, or for myself, and see if the certificate that I got from the server is one that I should trust. There's nothing actually adding it to these files. So if you have a certificate that you don't want to, or that you want to trust, you have to add it yourself. You'll get an error. You look at your log file and you go, okay, well, that's the cert I want. So great, that's wonderful, and it'll work as long as the public key of the certificates is actually stable. If the public key never changes, and it doesn't have to change, if you're issuing your own certs, you can just ask, give me a new cert, here's the key I used to sign it, give me another cert with that. And that'll work just fine for refreshing your certs. A lot of people using certs will generate a new public key every time they ask for a new cert. So the public key always changes. It's not stable, which means that every time you connect to, for example, Gmail, there's probably a 1 in 10 chance of it just saying, oh yeah, the cert's changed. Please try again. Or please, I don't know who you're talking to. It works if curating it manually is fine. It's tedious. You don't want to manually add your certs every time. This sucks. So, and also, not very many programs actually do this. I think this is the complete list of programs in the system that use that look at the thumbprint files, and this is a bit of a cheat because TLS client is a general program that's used for a ton of other stuff. So every RC script that will connect over TLS, like your IRC clients and so on, could in theory use a thumbprint file. It's not as we don't give a fuck as this list implies, but for example, if you're browsing through Mothra, we will just accept the certificate. We don't actually validate that it's talking to the right endpoint. We just validate that we get an encrypted channel. So, let's just say that someone does some DNS hijacking. We won't detect it. So how should we handle it? So the proposal that I'd like to put together is we look at factotum and we go, ooh, we should not put X509 in there. Let's put it into another thing. So we have another program that kind of mirrors factotum, but isn't factotum. Something that kind of sits in there and acts as an agent for validating certificate chains. So what we have right now is auth-PKI. It's a file system that handles, you give it the root store, you send it certificates, and it says, yeah, this one looks good. Yeah, that one's a mess. That one's, you don't want to talk to them. They're not cool. And there's a little protocol kind of, again, similar in spirit, but not the same as factotum, where you basically send it the cert and it gives you back the OKs. So the way it ends up looking is you open the mount PKI new, which creates a connection to the PKI service, and you write verify host name, where the host name is who you expect to be connecting to. Write cert and the number of bytes for that one cert. Remember, this is a cert chain, so you're going to need to put in a bunch of certificates. And the certificates may actually be, you may or may not need them all, who knows. So we write the cert and the number of bytes in the cert, or the actual byte, and then we write the number of bytes. We write cert, we write the bytes in the cert, and then when we're done with all the certs that we actually care about that are not part of the root store, we basically write verify, and we read back okay, or we get an error on the read. And that gives us the ability to know that we should be using this, or that the connection is okay or not. Relatively simple. The implementation of this is currently incomplete, but for what it does, it's about 800 lines of code. I'll talk a little bit more about what the complexities are. Specifically, what's missing, testing. I just put it together, tried it out. It seems to work. The big one, name verification. This is where the giant mess of verification ends up happening. I don't remember what RFC it is. It's something like 6293. It starts with a 6. 6125, thank you. 9618. Yes. Anyways, those are a complete mess because you have to understand the structure of the names. You have to know that, oh, this certificate is talking about emails. I have to parse out the email to verify the email. I have to parse out the URL and do whatever. I assume that I'd have to do the normalization for Punicode and all of that other stuff that should never have been put into the certificates. It should have just been a raw blob of bytes. I'm not the one designing these specs. I'm just the one crying and drinking way too much as I try to figure out what the hell needs to happen to make this work. And then there's a bunch of libsec and actually a couple of libc changes that need to be done to actually do, well, to be able to actually do the name verification. And specifically, what happens is, or the libsec API itself, right, TLS client at the moment, is unfixable. And the specific problems, it throws away the certs. So when you connect to a system or to a URL, it will grab the certs and throw away every one but the last one. So we can't actually verify the chain. It mallocs and frees on the client. So if we start keeping the entire cert chain rather than just the one cert in the that we care about, we'll start leaking memory, and it doesn't actually know the name we're connecting to. So, and then there's a couple of other things like mixing in and out params, which makes it a little bit confusing to use. And when I started looking at this, we found a number of bugs where we were just leaking a bunch of certs. So it's not a great API. What we'd like to do is make a couple of, and then the other thing is that we need to know the name that we're trying to verify. And by the time we've gotten the TLS client, we've thrown all that information away because we've got a dial string, we've got a file descriptor. Cool. What's the dial string for? What's the file descriptor for? Fucked if I know. So we need to figure out something else to do. And I'm kind of leaning towards either dialster parse, which would give us, well, it will either be dialster parse, which lets us parse the dialster and get the name out, or we just add a new spec to the dial strings. I like this one a lot more than this one. So being able to dial TLS bang whatever, and getting back a verified file descriptor would be quite nice. And then if we end up wanting to do UDP, we get, what was the TLS? MTLS. Sorry, no, MTLS is the wrong one. There's some TLS that's for UDP. We can, DTLS, that's it. Datagram TLS. So what the API I think I would like to get is a TLS client that takes a file descriptor serve and serve as the name that we're connecting to. Config params, TLS server, we mirror the same thing and we get, and then we free the params through a function rather than trying to tell the client, yeah, here's the list of things you should free. Just read the man page and do it right. And then the contents of these structs would look something like that, which scrolled off the screen, but yeah. TTLS, by the way, is a specific thing that's used by the WEP spec. I don't remember exactly what the first T stands for, but basically it's a keyed TLS. So you basically use WEP to get the key, and then you do some negotiation with that. So we need to support that. The client and then the server conf is, again, very similar. I think we actually don't need the TTLS here. Nothing would use that. We don't support WP servers, but if we need to, that we might. This this is all very similar to what we do in the TLS stuff, but in the current APIs, but it's not that different. But it's just cleaned up a bit, so we can actually separate out and know what we're passing into the function, what's coming out of it. And then finally, we've got the TLS params, which is what comes out of this. I think that's basically everything at the moment. The current state is that there's a proof of concept implemented. The verification is 200 lines of code. The file server is about 500 lines, and getting the name verification to work will probably end up taking another 5,000. So.
One nice feature you may want to have is to check.
Sorry, basically the place where this stopped is where I looked at the name verification. My eyes went blurry. I looked at the name verification again. I picked up my beer and walked away. But yes, I think something like that. The other thing I didn't talk about is search revocation. That's also something that this should be able to handle. We load up a CRL. One thing that we will never do is the online revocation, because that leaks information about what sites you're actually trying to visit. But being able to grab a search revocation list and maintain that, there's the open question of how do we actually keep all of this stuff up to date. There's the open question of, basically all of this is pretty complicated. Some of it's very needlessly complicated, some of it makes sense. That's why it's a work in progress. I haven't figured out what I can get away with not doing, what I need to do, and what would be a mistake to do.
What online is if you fix it once, you fix it for the whole system. So this is very, very much worth doing.
Yeah, and this is the other thing. The big chain, the idea with the TLS bang in Nile is that you can actually, nothing actually needs to know about the new TLS APIs. It's just we start using a new dial string and everything is cool.
All right, so I have a question. Hasn't it struck you that each certificate can only have one signature, unlike paper documents, for example, or anything sendable?
I mean, it can be signed. I guess in theory you could sign a certificate with multiple. Yeah, I don't know.
All right.
With the Web of Trust, you can.
Yeah.
Certificate authority is one model of PKI, but the Web of Trust is another one, which is used, for example, by the Debian project to type pages.
Yeah, but does it work with X509?
No, it's a separate norm, but there you have multiple signatures. Yeah, no. There.
Yeah, X509 just has the one field in the cert.
There is cross-signing in X509, just so that you know. We can talk about that over the weekend.
Yeah. Oh yeah, that is the other thing I am definitely going to admit. We can do client certs. This has nothing to do with PKI. Cool. I think that's it.
All right, well, good afternoon to everyone who is there in person in Paris. I'm sorry I couldn't be there. And good morning to those who are watching online from North America. As I think most of you know, I'm Brian Stewart. I'm on the faculty at Drexel University, and I've been involved with the Plan 9 community now for a number of years. I got to thinking about it and realized it's been about 30 years since I ordered the CD and manuals that make up the second edition Plan 9 distribution. Though from software perspective I am mostly a systems guy, my research over the last several years has been primarily focused on the history of computing, particularly the ENIAC. Now, the ENIAC is a machine that was built at the University of Pennsylvania during World War II, and it was built literally just a few blocks from my office. So between that and proximity to the archives at the university, I've been able to take quite a deep dive into this machine, and it's been quite a fascinating journey. Part of this work has resulted in a simulator of the machine. Now, the simulator in its core is written in Go. That makes it portable, obviously, to a wide variety of environments. Depending on what environment it's in, different modes of visualization can be applicable. What I'm going to talk about today is some interfacing, visualization, and control interfacing that works on a Raspberry Pi under Plan 9. Now, the control box itself that we're going to talk about, well, this is a device that they could carry around the room with them. Now, the machine itself was literally a room. The space in which the operators could work was 32 feet by 16 feet, or roughly 10 meters by 5 meters. It was needless to say, a fairly large machine, and so if I wanted to go and clear something, initiate something, single step, it wouldn't be very effective to run across the room for it. So they had this portable control box with a cable long enough that you could carry it around the room, and it duplicated functionality that was on the main control panels of the machine. Now, the box itself, I have not found an engineering drawing of the original box. What I have found is one photograph, and from that photograph and doing a fair amount of pixel counting, I've put together this 3D printed model that I believe is quite close to the original, but I can't be certain. Though I will point out that there was one bit of a brain fart in designing it. The cable on the real one comes out the bottom, not the top. Now, on this box, the toggle switch here has 3 positions that can be used to control different clocking modes that I'll talk about in a moment. And then these 4 buttons are push buttons, momentary contact push buttons, that are used for initiating certain operations within the machine. Now, the clocking controls give us these 3 options: a continuous mode, a 1 add time mode, and a 1 pulse mode. The clocking of the machine is based on a master 100 kilohertz clock. That clock is divided into segments of 20 pulses, and each group of 20 pulses constitutes 1 addition time. This is the basic operation of the machine, somewhat analogous to executing an instruction on current machines. The continuous mode lets the clock free run. It's the way you would normally use it for doing calculations. If I set the switch in the 1 add mode, then I can use one of the push buttons to single step the machine 1 addition time per push. So it's effectively like single instruction execution. If I set it in the 1 pulse mode, then the pressing of the button is 1 of the 100 kilohertz pulses. So you can watch the execution of an operation step by step through its progression. The 4 push buttons, the first one is the clear button. Now this sends a signal to all of the accumulators to reset them back to 0, and it also resets any other counters that are involved back to 0. The reader start and initial pulse buttons are used to initiate a computation. Now, which one is being used depends a little bit on the design of a particular computation. Some computations begin by reading a card from the input and then processing the data on that card. Others begin with computation rather than reading input, and so the initial pulse switch handles those. The 1 pulse 1 add button is the single step button. In the 1 add mode, pressing it does one group of 20 of the 100 kilohertz clock signals, and in the 1 pulse mode it does 1 of them. Now the station itself is connected in terms of our simulation to the Raspberry Pi pretty much in the way you would expect, i.e. GPIO lines. And the Plan 9 interface to these GPIO lines is in the form of a read operation. Here we're reading, and in doing that read, you get all of the GPIO lines in one read. I should point out this is the version that is distributed on the 9legacy.org site. The 64-bit value that comes in is represented as 16 hex digits. So we're going to read a 16-digit value, convert it to a 64-bit integer, and then use bitwise ANDs to look at the state of the specific GPIO lines that are connected to each of the individual switches. Once we recognize from the pattern an operation that needs to be performed, then what we do is we essentially pass a string, which would be the same as the string that a user might type at the command line interface to carry out the same function. For example, the clear button. For debouncing purposes, we do the reads every 10 milliseconds, and then we don't don't operate on a given measure or reading until we see 4 in a row that are all the same. So when we see 4 in a row that match, we now look at it, compare it to the previous stable reading that we had, and now we ask, does this represent a change that needs to be sent as a command? The code for doing this basically looks like this. We have our 10 millisecond wait, we read the 16 bytes, we turn that into an integer, and then mask off and look at the bits to figure out what to do. Now, I'm only showing an excerpt here. The only one of the commands that I'm showing at this point is the one that recognizes the pressing of the clear button. So that call to proc command B space C is sending the B space C command, as one might type at the keyboard, to the command handler. So that's the control station part of it. In a lot of ways, for this particular bit of work that I'm talking about, the more interesting part is the display. In specifically an LED array. Now, I'm using here an off-the-shelf matrix that is 16 rows by 64 columns. The way it's made is out of a group of 8 by 8 monolithic LED modules. These modules are then soldered into a board that has circuitry on it to present an interface to this 16 by 64 grid. The way the interface is structured is there's a 64-bit shift register. That represents then one row of LEDs. The shift register chips involved also have a latch on them. So you can have a stable output while you're shifting in a new group of 64. You pulse the latch signal, and then it copies the values from the shift registers into the latches. Those latches then are connected to one side of each LED within a row. So a given position of the shift register will be connected to all of the LEDs in a column. To select which of the rows we're looking at, we have a 4-bit decoder. The particular board I'm using, this is implemented actually as 2 3-bit decoders with a 4th bit selecting which of the 2 decoders is active. But the effect is we have 4 input lines and 16 that represent the output of the unique states of the 4 bits. There's an enable line also that's gating that row selection, which then connects to the other side of each LED. So in effect then, by selecting a row and setting a bit in a column, you are turning on or off a given LED. The effect of this obviously then is that we need to multiplex the display by showing one row at a time and cycling through that. And if we cycle through it fast enough, then we will have what appears to be a stable display. This is something we're pretty familiar with. Now, the basic algorithm that we're going to go through is this. We're going to transmit our 64 bits over the SPI interface. It turns out that the characteristics of the shift register chips in terms of polarity and phase of the clock matches mode 0 of SPI, which also happens to be the default mode on the Raspberry Pi when you bring it up. So that's going to be how we send a row of LED values. 64 bits then, of course, is 8 bytes, so we'll be sending a group of 8 bytes, loading up the shift register. Then we're going to turn off the enable. So while we were shifting it in, we had one row of LEDs that we're displaying. We're going to turn that row off, latch the new 64 values in, set up the address, and then turn the enable back on. And finally, deassert the latch. The deassertion of the latch can be done, in any number of places. It just kind of makes the most sense to do it while you're leaving the LEDs on. Now, the code for doing this looks essentially like this. There have been a few different variations on how this is done, but this is the basic model. The first line there is the writing of the 8 bytes to the SPI interface, and then the sequence of prints there doing various set operations on the GPIO lines is carrying out that sequence of pulsing the latch, turning off and on the enable, and setting up the address lines. And then, of course, we finally increment our row number. We have a sleep 1 here, which I'll say just a little bit more about in a moment. Now, there are several different ways you could structure this. Perhaps the most natural way that most of us would think of is, I'm going to periodically refresh the whole display. The thing about that in this scenario is you end up with a very quick refreshing of the display, and then you turn around and wait a period of time with nothing turned on before you refresh it again. The effect of that, well, it amortizes the work across that, but it unfortunately leaves the LEDs off most of the time. Now, the effect of that is relatively dim illumination, which from a purely realistic simulation perspective isn't really all that bad, because the neon lamps in the original machine weren't particularly bright. But for the purposes of having something for exhibiting and showing people and explaining how the machine works, it'd be nice to have those things a bit brighter. So the next approach is, okay, let's do it where once a millisecond, I update one row, leave it on for the millisecond before I update the next row. And that's essentially the code that you saw before. Now, if we do that as an ordinary time-shared process, this has a little bit of an issue that comes up, particularly when the simulator itself is running, because the simulator is quite compute heavy. There are a very, very large number of channel messages being sent, and that eats up some amount of CPU time. And so you end up with a display that has a tendency to kind of flicker and blink, and it's not a good, solid, steady display, unlike the real ENIAC, where the neon lamps would be quite solid. So the next step in development was to say, okay, let's use the real-time scheduling mechanism of Plan 9. In this case, what's going to happen is that sleep that we have here at the bottom, it'll become a sleep 0, which effectively means yield. And then what we'll do is we'll configure the scheduler to say, schedule this thing once a millisecond. And the way we do that is this. When we create the process, we're going to open its control file, and then we're going to send a sequence of messages. The way you do this in Plan 9 for a real-time process is you first write messages that configure the parameters of the real-time scheduling. In this case, we're setting the period and the cost both to 1 millisecond. And then you send the message admit. When you send the admit command, it goes through and checks the parameters that you've set and says, does this set make sense for a useful real-time process? If it does, the write succeeds and the process is put into the scheduler. If, on the other hand, the set of parameters do not make sense, then the write fails. So even though I'm not showing it in this slide, in the real code, I've got a test on the fprint printing the admit message to see whether it succeeds or not, to make sure that I have configured the real-time scheduler in a way that will actually function correctly. Now, it turns out that the real-time scheduler works generally quite well, but not perfectly. If there's nothing else going on the machine, scheduling it once a millisecond is generally quite reliable and you get a good solid image. And I should mention, by the way, that the rate at which we're updating is somewhat critical. My original thought had been, if I can update the screen 30 times a second, that should be good enough. After all, movie film classically was 24 frames a second. NTSC television, each half of the interlacing was a 60th of a second, so the full frame was done every 30th of a second. However, those environments are ones where there's enough persistence that it turns out that you can kind of get away with a little bit slower than you can with these LEDs. It becomes very noticeable that there is a blinking effect going on at 30 frames a second. So 60 frames a second is pretty much necessary here. So this means then that the 1 millisecond per line is a fairly important number. But if the system is heavily loaded, even with the real-time scheduling, you can still sometimes see some flickering. I'll say a little bit more about that later. But for that reason, the next experiment was to write a kind of minimal device driver in the kernel. And this device driver really doesn't do much more than hook into the basic timer and say, wake me up every 100 milliseconds. And then it does the update of one row. So the code for that looks something like this. Now the bottom part of it is essentially the same as what we had before. That is, these calls to GPIO out are carrying out the same operation as those fprints were doing the set operations. The top half of this is essentially just the write to the SPI port. Now, this turns out to be slightly more involved. In the code itself, there is, when you do a write to the SPI device, a call to a function that initiates a SPI operation and then unblocks the process when the SPI operation is complete. But I can't use that here. The reason is that it uses the DMA controller and waits for an interrupt when the DMA controller is finished. But because this is tied into the timer, this is itself running in an interrupt handler. And so once you're in an interrupt handler, you can't block waiting on an interrupt. So this is actually recoding the guts of the SPI interface to do polling. The polling is kind of interesting here as well. It turns out that in order to know when the next byte you can write is, there's a bit that tells you it's ready to take another byte. But that bit's not the same bit that tells you it's done writing all the bits. And so what happens is, when we're writing 8 bytes, we look for the one bit 7 times, and then after we've sent the 8th byte, we look for the other bit. And that's why that loop is structured the way it is. So it's a little bit weird, and you'll notice that we've got these 2 while loops that are going to just spin waiting on the bits to tell us it's time. You might be concerned, at least I was concerned initially, that this might take a bite out of the system's CPU time. It turns out it really doesn't turn out as bad as I had feared. In looking at the statistics reported by the kernel, I find that it actually is only it's only increasing the amount of time spent in interrupt handlers by about 1%. So, you know, if it was already at 1 percentage point, this bumps it up to 2 or something like that. So it turns out to not be nearly as problematic as I was afraid it might be. And as a result, then, it actually does function pretty well. Now, what I'm going to do next is I'm going to kind of show you the whole thing in a demonstration mode. Before I do anything else, though, I'm going to mute the audio so that it doesn't create nasty noises as I move the camera. Okay, so this is the 1/8 scale 3D printed model of the ENIAC. Up here is where the LED display is located, and then there are 3D printed baffles in front of it to allow through only those LEDs that we're actually using. So I'm going to start by running the real-time priority version of it. For time, I'm not going to run all of the different versions. Now, this one is, as I said, running the real-time scheduled version. So it actually looks fairly good in this presentation, partly because of the responsiveness of the camera, and partly because as the display is being moved, it's less obvious when there's flicker going on. To give you a little idea what's going on in terms of the operation here, I'm going to go ahead and shift it to the one add mode here. And now I'm going to carry out some operations. Actually, this is the one pulse mode. So if I do it to the one add mode, you can see it doing various steps. And there it is back at full speed. Now, even though it's not very easy to see here, as I said, there is a certain amount of flickering that does occur even with the real-time scheduling. So what I'm going to do now is switch it over to the, oops, I'm going to have to reset this keyboard. I believe it's a power supply issue that sometimes this keyboard will basically die on me. Okay, now I'm going to restart it running with the kernel driver. And there it is running with the kernel driver. Again, unfortunately, because of the nature of the camera, the frame rate, all this sort of thing, I'm not able to really show the difference very well. But it's still an interesting one that I want to investigate further. So let me go ahead and stop this and get back to the presentation. So this, as I said, it was kind of an interesting thing that came up, trying to understand why the real-time handling didn't necessarily give us a good way of dealing with millisecond level resolution. I have a conjecture about this. I don't know for sure what it is. I haven't really had time to dig into it yet. My suspicion is this. When a real-time process is released, it gets put onto the ready list as you would expect. It appears at the highest priority on the ready list. But I don't think that it immediately preempts a running real-time time-shared process. So because time slices are several milliseconds, that means that a real-time process might have to wait a few milliseconds before it can actually do its thing. And for something that's meant to run every millisecond, it's possible that this is causing a delay that's enough to create this flicker. I don't know for sure that that's what's happening, but that's my suspicion. I do have a student who has indicated an interest in doing a research-oriented senior project. And so we're looking at possibly digging into this more deeply. A couple of things immediately come to mind that we would want to look at. One would be to, first of all, look at the way the scheduler is designed and verify this question of, does it in fact preempt immediately? And if not, what would be involved with actually doing that? An alternative that definitely seems like kind of an interesting one, especially now that we're in a world where virtually everything is multi-core. What if we reserved one core for the real-time processes and the interrupt handler? Let the other cores, in this particular Pi that I'm running, that's 3 other cores, let those be used for all the time-sharing processes, and then have the one core reserved for the real-time activities. Don't know yet how well that would work, and I don't know how much surgery is going to be required on the kernel to do it, but I think it's going to be an interesting avenue of study. So that's where I plan to go with this, and I'll be glad to answer questions that anyone has. Thank you.
right, and now comes the interesting part where we're gonna have Brian on Google Meet, and if all goes well, look, we already see him here. All right, and I need to unmute myself here. Hello, Brian, can you hear us?
Yes, I can indeed hear you. Can you hear
Excellent.
me?
And we can also hear you, and let me see if we can also get both audios in the recording, and it looks good. Alrighty. So,
All right.
should there be any questions, please come up here and take this beautiful microphone, and we get the camera here, so you get a picture as well. Just send here. Symbolically, that would be where somebody asks a question. Does anyone have a question, actually?
Don't worry, my feelings won't be hurt if nobody has a question.
Yeah, we're getting there. It was coming. Thank you so much for volunteering.
Yeah, the reaction in the room was to ask you to coordinate with Ron and his team with Nix, because you can get like a core for your process can have his own core and do its stuff without being bothered by the kernel or whatever. And
Yes,
also, I don't. Yep, sorry, go on.
Yeah, I definitely think that's a direction that I want to look at, is looking to see if the Nix work would make sense here.
Sleeping for a constant amount of time is not a very good idea. Maybe you could like see how much time you have left and sleep only that amount of time, like a game loop.
Right. And that, in fact, does make sense, and I do it in some other stuff that I've done. The only issue here is that I would have to go to a different form of the sleep mechanism, because the sleep call is in units of milliseconds, and I would have to then go down into a sub-millisecond kind of resolution for that part of it. But yes, I did think about doing that. It's just that I would need a different form of sleep.
Also for the flickering, if you do that, I think you can skip frames. Like if you are late, you don't have to do all the frames, and maybe that could stop the flickering. Even if you are interrupted by the kernel, like you can drop the last 3 frames and go on with your life. And I don't think it will be noticeable by the naked eye, just looking at the LEDs.
Yeah, in fact, the updates that are happening inside of the simulation are faster than we're updating the screen anyway.
Yeah, I had I think a similar question. Like the hardware is so cheap, and these microcontrollers are so cheap now that it seems like you could not worry about like shift register or do the shift register thing, but that's actually just giving the data to some microcontroller that's going to keep track of the display until you're ready to tell it, okay, go to address a different location.
Certainly that could be done. I'm kind of treating the Pi as dual purpose in this regard, being the microcontroller for that and also running the simulation. But you're right, I could very easily connect a lower performance device like a Pi Pico or something and have it control things.
Do you have original ENIAC programs, or do you have to write your own?
Well, that's an interesting question. There is a very small amount of recorded ENIAC programming out there. It seems that they didn't do a lot of keeping and hanging on to their programming. There's a lot of references to, oh, we did this, but nowhere do you actually see the exact configuration of the machine that they did that with. There have been a couple of papers written, in fact, that have attempted to reconstruct ones. There's one that I and some students are working on right now, that we have a fairly complete diagram of the wiring of the machine for the problem, but what we don't know is, was this the kind of initial version of it before they started trying to do any debugging? Was this the final version of it? And in later papers that were written about it, there have been mentions of a couple of different kinds of bugs, and we don't know for sure if they were ever resolved. So the reality is there's a lot of open questions with respect to that.
We got one more question coming up.
Sorry. Can you tell us a bit more about the program you showed us running? Because I was under the impression like one row should only have one light because it's 10 lights and it's a digit. So why do we have a line full of light? And you see what I mean?
Yes. So let me first of all kind of characterize what the array of lights is actually saying. Each of the units that we saw, there were 4 in this model. Each of those is an accumulator on the machine. Now, each accumulator can store 10 digits. Now, the position of the illumination vertically is telling you the value of the digit from 0 to 9. And then horizontally, you're looking at the 10 different digits. So at any point in time, you should see exactly one illuminated LED in a column, but then there will be a total of 10 across the line. There's actually one extra pair all the way over to the left. That is the sign of the number. So that's what you're looking at. The particular programming that was running in the little demonstration was just a simple number theoretic problem that was searching for all of the 3-digit numbers that are equal to the sum of the cubes of the digits. And you were seeing 4 of the accumulators that were involved in that. There's actually a total of, I think it's, if I remember right, 14 accumulators being used in that problem. Or 11, I forget.
All right, we got one more question coming up for you.
Okay.
Hello, I have a question about the history of computers and evolution of, the evolution of computers.
Mm-hmm.
So, if I look back at a lot of the old papers I read, clearly they, you were talking about scheduling and cores, dedicating a core to real-time workloads. What are, let's see, how do I formulate this? In your view, what things have changed a lot from a hardware and software perspective? But really the software hasn't changed. The software hasn't adapted as much as it should have. Perhaps it's we should take a different approach to scheduling or memory management or IPC or other things. But in practice, we're stuck in the past. So what things would that be?
I think you really kind of hit the nail on the head at the beginning with that. It really, I think the biggest difference is in the amount of parallelism we have now. We spent pretty much the first 70 years of the field living in a world where if you had more than one CPU running concurrently, it was an unusual situation. And we spent a lot of time in the 80s looking at what are the different ways we can interconnect these CPUs. Nowadays, we're kind of living in a world where we've got a substantial number of CPUs. Even on a tiny little Raspberry Pi, we might have 4 cores, all sharing the same memory space. And I don't think we've done a lot of thinking about what is the best way to utilize that kind of functionality. The ironic part of this is that the ENIAC was originally a very parallel machine. Each of those accumulators could be doing something simultaneously with all of the others, and there were a total of 20 accumulators on the machine. There's a mathematician by the name of Derek Leamer who had done some really interesting stuff on the machine doing prime number work. He actually created a sieve to generate prime numbers, and it worked in parallel. So it basically tested divisors in one step. And in a later conference, he made the comment that the ENIAC was a wonderfully parallel machine until von Neumann spoiled it. But the funny thing is that there are also comments by, like, Press Eckert, he was the main engineer on the machine, where he later said, okay, we're going to focus just on things that are serial because programmers find it so difficult to understand and manage the parallelism. So it's been a very interesting evolution in that regard. And I feel like we're still kind of in the early days of understanding what's the best way to think about and use the fact that the reality is going to be parallelism is going to be to our advantage.
Thank you. All right, so that's it for this talk. Thank you again very much. And I hope we can find somebody to get you this beautiful trophy here.
Yes, I would appreciate that. We can figure out a mailing address, either that or sometime we'll find a way to do this.
Yeah. All right. Yeah. Thank you very much again.
Thank you.
All right, so yeah, next up we got Jeff Collier about the evolution of Plan 9. And this is also a remote and pre-recorded session.
Years to Unix. At the time, it was quite a shocking system, and pipes were a really novel invention. A lot of the features that were new and novel in Unix then are commonplace today, but at the time, it was quite a revelation in operating systems. So I was an undergraduate, and was introduced to Unix by a high school friend, Eric Giesen, who had gone to the University of Waterloo instead. And he let me try out the Waterloo system. I persuaded my department to get a Unix license for 6th edition. And then Charles Forsyth helped us upgrade it by providing a lot of the work that had been done at Waterloo. It's important to understand that other systems of the day were used considerably larger machines and were a good deal less interesting. So Unix was a real contrast. Ran on smallish hardware, at least at the time, and provided much more elegant and interesting service, I thought. So I followed the progress of Unix through 10th edition. The Unix vendors of the day, this is the late 80s, were making a mess of the system. And I went to interview with Rob Pike in 1986. Actually, no, I went to interview with Bell Labs in 1986. Rob was one of the interviewers. And that was the first I heard about what was to become Plan 9. He was developing software for the NOT terminal, which was a successor to the DMD 5620 in that family, but with a network interface and a virtual memory operating system. A year later, Rob gave a talk at the University of Toronto where I was on staff, and I found it quite inspiring. The vision he presented was essentially that of a Plan 9 terminal. You boot your terminal and you import resources, devices, what have you, from the network, and customize your namespace with those. And then the UK UUG papers were published, and that was, to me, almost as big a jolt as the 1974 CACM Unix paper. It seemed to me that Plan 9 was a continued evolution of Research Unix, but for modern hardware, with the benefit of 20 years of experience, different where it made sense, and designed for distribution. Not necessarily over just Ethernet. It was somewhat network agnostic, and the initial terminals were not. Rob was giving out a single floppy bootable PC distribution at an early 1993 Usenix conference, and I managed to get one, which again was provided a sort of a taste of what the system could be. So in 1994, I came to Bell Labs to work for Ted Kowalski of FSCK fame. He was developing a set-top box called Home Center, and I was providing the operating system for it. We did that. They started making them. Second edition of Plan 9 was issued the next year for a nominal fee, ran on sort of current hardware of the day. Some of the components were built from the LF language, notably the 8.5 Windows system in Acme. In 1995, also, AT&T split. Home Center was canceled. I moved into Research Unix support in Lucent, the new company. And most of what had been Center 1127 Computing Science Research moved to Lucent as well. So the initial IBM PCs were solidly uniprocessors. And some companies like Sequent, I think, and certainly Compaq tried to make multiprocessors out of them. The Pentium Pro was the first one really designed for more than just two processors. And the memory ordering model from the 486 on has been the same according to Intel. But starting with the Pentium Pro, the CPU pipelines and store buffers became long enough to cause problems for Plan 9 sleep-wake up due to the queuing of memory writes. So that got sorted out by Dave Prezzato and Jim McKee mostly. A little help from Intel. Intel guarantees cache coherence, though not DMA coherence, amongst the x86 CPUs in a multiprocessor. And the problem is worse on essentially RISC CPUs that require manual cache flushing. The early ARMs, before V7 certainly, PowerPC systems and so forth. RISC-V systems nowadays tend to provide cache and DMA coherence, which is really, really nice. So, one of the things going on when I first joined the labs was Brazil being driven by Phil Winterbottom, partly to try to make the system more efficient, but also to try some experiments, including uncompressed raster graphics. That ultimately got replaced by DevDraw. And yeah, that's eventually Brazil became merged into the main line of Plan 9 before third edition was released. Inferno was a response to the needs of set-top box developers. So it was essentially a Plan 9 kernel with user mode processes replaced by a Limbo bytecode interpreter. It could run on some bare hardware, mostly PCs, or hosted on another OS, including even Windows. Limbo was the primary language for writing applications, influenced by CSP and LF, and the dev-draw interface first appeared there on Inferno. In 1996, I moved to a research department building a multimedia message system named Mesa, which incorporated fax, mail, and voice input and output and conversions amongst all of those, notably OCR faxes, and the ability to take commands by voice. It had no artificial intelligence, deliberately, but a number of people found it quite useful internally, both as a way to dial people. They could look them up in the corporate directory, and also to save voicemail when people called them. So Mesa was based on Inferno, which in turn was hosted on Xeon PCs. Also during that time, I designed and implemented an SMTP replacement called RSMTP. So at about this time, we moved to 100 megabit Ethernet and also switched Ethernet. 100 megabit made switched Ethernet made a much bigger difference in performance than going to 100 megabit. The combination of them was quite nice. Made the network really much more pleasant to use. Phil Winterbottom started a project called PathStar, which was meant to be a combined telephony and IP router, which might have competed with the number 5 ESS phone switches that we typically found in central offices, at that time at least. It was built on a Plan 9 kernel, but ran Inferno. In 1999, my department moved to PathStar, hoping that a Siri-like replacement would be an appealing thing. Siri-like replacement for dial tone, that is, would be an appealing thing. And then in 2000, PathStar was canceled. Phil and Ken Thompson left Lucent, and then in 2001, the dot-com crash happened. They sort of all happened together. I think that's the sequence in which things happened. It was kind of collapsed in my mind into one thing. The Inferno business unit couldn't figure out what to do with Inferno. So they sold it to Vita Nova, Charles Forsyth's company, who went on to make a really serious effort to promote it. Now, once Phil had been the maintainer of the LF implementation, compiler, etc. So when he left, it was replaced in a sense by the addition of a libthread in C. And with that, third edition was issued in 2000 under an open source license. A new version of IP, 9P, our file server protocol, named 9P2000, was created, and Ken's file server kernel was adapted to speak it or the old original 9P, now called 9P1. And a few system calls had to be changed to accommodate the new protocol, including a new authentication mechanism, which was supported by Factotum and Sextor. And then Sean Quinlan and Sean Dorward created Venti, a hash address block store which provided deduplication as a side effect, essentially. So third edition, I believe, included all of those things, but it was rather a rudimentary version of Venti. In 2001, Lucent offered to buy out a lot of the senior researchers. Rob and others left for Google. I left for a startup in California. And then fourth edition was issued. Again, with a fairly rudimentary version of Venti. Sean Quinlan, Jim McKee, Russ Cox created a new user mode file server, Fossil, that could use Venti as its block store or could use a disk partition. If you use Venti, you get automatic backup in history and versions and versioning and so forth. I was writing early gigabit Ethernet drivers and bought my own optical jukebox. Venti and Fossil were still pretty new, and I didn't want to rely on them yet. But I wanted to be able to manipulate archives that were bigger than 2 gigabytes. So I modified Ken's file server kernel to implement 64-bit file and device sizes, and I think tripling direct blocks. And a few other people picked it up. And it eventually got turned into a user mode thing. We'll talk about that later. It was feasible in large part, well, in part because Bruce Ellis had greatly improved the code generation on the 386 of most VLONG operations, inlining them, which made their use cheaper and I would argue feasible in that context. I also implemented gray listing in SMTPD because I was getting a lot of spam at home. And then in 2004, Dave Rosato left for Google. I bought a used Alpha PC and ran Plan 9 on it, 32-bit port, despite being a 64-bit processor. Dave Hogan had ported it while at the University of Sydney before he joined the Inferno business unit. It was a fast machine for its day, although power hungry. And every model of Alpha was somewhat different. It had loadable microcode that varied with the operating system. The method for accessing the serial console varied with every model, I think. So there wasn't a single porting target that you could use. You pretty much had to pick a single model and port to that, and perhaps if you were lucky, some other model might be not too different from that one. 2006, Alcatel bought Lucent and became Alcatel-Lucent. Jim McKee recruited me to return to research, to what was left of what had been Center 1127. Russ helped me get the latest Venti, now using libthread, to work and to survive restarts. It had been destroying its block store when it was restarted, I think due to a too small thread stack overflow, if I recall right. So once we had a reliable Venti, I then copied the contents of the old optical jukebox file servers into a Venti store, which was initially on a RAID 5 volume on magnetic disks. I don't think at that point we were using the co-RAID device. That history goes back to the end of February 1990, so it's not the very beginning of Plan 9, but it's fairly early, at least from my perspective. I then converted the old file server kernel that I just talked about into a user mode file server, retired the file server kernel and the IL protocol because the file server kernel had been the last software that really relied on IL. And we wanted to have fewer kernels to maintain. Jim had long maintained the PC kernel support, and he created the 64-bit 9K kernel for a U.S. Department of Energy contract. Charles Forsyth produced the C compiler for it, and ultimately the project decided to not use AMD 64s, but to use IBM Blue Jeans with Power PCs. These are supercomputers at various government labs. And those labs only had 10 gigabit per second infrastructure. There was just no other, apparently. You couldn't even plug in a gigabit interface. So we acquired 10G interfaces and drivers, and then we needed a switch to plug them into to test this stuff out. We just could not get one through the internal processes. I banged my head against it for quite a while. Couldn't get a 10G switch through the internal purchasing process. So finally I called Arista Networks, I hope I've pronounced that right. And the salesman said, some of the guys are afraid you're going to take our switch apart and reverse engineer it. So I had to really promise and beg that we just needed a working switch desperately, because we couldn't buy one internally, that we really would not reverse engineer it. And after a lot of pleading, as I recall it, we got our switch. 9K initially only ran on actual AMD 64s, not even Intel 64 systems, although I eventually fixed that. Tended primarily as a CPU server for use with draw term or other terminals. Largely compatible with Plan 9. I did a bunch of 32-bit ports, mainly looking for something that portable and small that we could carry around and plug Ethernet and mouse, keyboard, and monitor into when we were traveling to other Plan 9 locations. We also had a 24-core Xeon system, probably in conjunction with that same government project. And I found that doing a parallel muck of a kernel on that used so much system time that it was slower than just using 4 processors. We now use semaphores for locking and monitor M-wait for idling, and I think that has probably fixed it. I don't have a 24-core system on hand at the moment, but I believe it probably has fixed it. There were a lot of bootstrap programs proliferating, I noticed. They were getting to be too big to fit in the bottom of memory on the PC, and so I created new ones from a variant PC kernel that used normal PC device drivers, again reducing our maintenance load. And the new bootstraps are compressed with LZIP. They decompress themselves when they start running, and they can load 386 and AMD 64 kernels. I was a fan of IPv6, tried to improve the support within Plan 9. I think it's reasonably good at this point. We don't do IPv6 DHCP, but I haven't needed it yet. And in 2011, Dennis Ritchie died. He was a friend and a major supporter of Plan 9 as well as Unix and C. And I think he managed to keep C fairly small and simple, at least through the first ISO C standard. Yeah. So in 2014, I moved to Google in Mountain View, California. Alcatel was then shortly after bought out by Nokia. So I bought a pair of TS140 Xeon servers, nice little relatively cheap machines with PCIe slots. They had an integrated Ethernet controller that I could never get to work, but I could add my own. And I got interested in NVMe. I did a driver for that. I wanted to explore 10G Ethernet some more. The initial Intel cards, the X540s, ran really hot. It was always a pair of controllers on the card, and it required cooling. And the TS140s had really loud fans. So in 2019, partly to save my wife's sanity, I bought a pair of quiet Puget systems, Xeon machines, and several little PC Engines APU2s, and got 9K working on them. So the 9K that I took from the labs was from 2014. It needed some work. Had to, make it run Intel 64s, fix some odd traps it was getting, upgrade the drivers, and most importantly, I think, make it capable of really using oodles of memory. So my intent here was to give lots and lots of buffering to Fossil Inventi and see how that works, and it works nicely. So I widened the malloc and memset size arguments to be of type uint pointer. This is a no-op on 32-bit systems, so it's a safe thing to do. And I adjusted Fossil Inventi then to exploit basically as much memory as they could they could get. Not every last bit of it, but a big chunk of it. And I have run those CPU servers on machines with 4, 16, 32, and 64 gigabytes of RAM, so I can confidently assert that it works on all those sizes. The 9K file server has been run, is still running on a 32 gigabyte system. There were still a few programs that now on 64-bit systems had too small thread stacks, and I think I adjusted libthread and some of the applications and libregex to try to avoid large thread stacks. A recent fix from Russ has even allowed us to run GhostScript on AMD 64, which I never thought I would see. It's just so baroque and broke and rococo. Nowadays, the kernels I'm building are probably smaller than they were at the labs. I don't put in every driver. I don't put in 10 gigabit Ethernet driver, or sorry, 10 megabit Ethernet drivers, or 100 megabit Ethernet drivers mostly. So L-zipping the kernels themselves allows them to be directly PXE booted without using 9boot or 9load or anything. On a lot of PC hardware, you can discover what you've got by looking at the PCI buses. And so planline.ini is usually not needed. If it is, you can still read the /cfg/pxe file for your machine if there is one, once the kernel is running. Future times. 2038 is not that far away, and 32-bit times are going to go negative in that year. I've converted the system to use ulongs instead of longs for times, adapted the libc functions that manipulate times, and a few programs that care. The tests for failure of things like the time system call now compare exactly with -1, not just any old negative time. That extends our times to 2106 without having to change all sorts of disk formats, particularly Fendi and Fossil, and I extended the time zone files for North America because I knew the rules for North America. I'm trying to rely less on APE. It used to be that awk invoked SH rather than RC, so you had to have APE working and building in order to build a kernel with Mach. And I've changed that, so my awk now uses RC. I can build a kernel without having APE working yet. Converted most of the other 8 programs, TROF and Friends, to be native programs. I think only programs that use Unix's select system call really require substantial changes, and I haven't converted any such programs. I also haven't done the PostScript programs or bzip2 or GhostScript, Spin, and Tech. Don't use bzip2 and Spin or Tech. So not a huge loss. In 2020, Jim McKee died. He was a friend and comrade in the trenches working on PC stuff. He'd been more or less cheerfully dealing with some of the most awful old PC capabilities of the CPUs and the surrounding supporting hardware from the very beginning. Wrote a lot of fairly tricky code that I am glad I didn't have to write. And in 2020, the Plan 9 Foundation formed. I wasn't involved in the formation of it, but I was asked to be a director. So I served a term as director. During that term, we persuaded Nokia to transfer the ownership of Plan 9 to the foundation, and we've made the historical releases available on the Foundation website, relicensed under the MIT open source license. Lately, I've been working a lot on RISC-V systems. I've got a previous paper about that. Richard Miller did the compiler suite, extended his existing compiler to 64 bits for me. Hoping that someday we can get off of x86 systems for our servers and including file servers, and use something simpler like RISC-V. We had contact with ETA over Ethernet, but not really much to do with the software. And I was aware that there was a NIX development path for a modified 9K that I didn't really pay a lot of attention to. I don't like jumbo packets. I think they're a really bad idea for sort of the obvious reasons on the slide. What I have done at home, perhaps as an alternative, is to negotiate up to a larger RPC size. I doubled it. And with that, I see about a 30% improvement on large copies. Yeah, Plan 9 is a distributed system. I don't feel that we need a web browser on it. We can run in web browsers elsewhere. Writing a browser is essentially infeasible, and C++ is just beyond comprehension at this point. People I worked with or watched work were generally pretty brilliant and generous folks. David Ducolombier has incorporated some of my changes into Nine Legacy, and Adrian Grigor, I hope I've pronounced his name right, is preparing a bootable installer image of my current system. Plan 9 hasn't taken the world by storm, alas. UTF's been successful, and there have been byproducts, Plan 9 ports, and re-implementations. But I think some of the most interesting and powerful parts have not been generally understood, notably the CPU command and the machinery that makes it work. Notably, TLS is a kernel device. It means you don't have to have special TLS read and TLS write functions in every program that makes use of the network. You can hand a process a descriptor that goes through DevTLS and have DevTLS handle the encryption so that naive programs can nevertheless use encrypted network connections. Operating systems are somewhat religious. I'm going to skip over this. I'm hoping that people will eventually absorb some of the better ideas in Plan 9. It took a long while for even some of the ideas in Unix and its predecessors to be understood, including things like /proc, which in Linux became a dumping ground for all the synthetic file systems for a time. And of course, we must defeat Git. Thank you. The paper has a couple of pages of references. These are not just padding. They're further reading. Some of the references are a bit obscure. Some of the events go back 50 years. Some of you may not have lived through this stuff. So if you want to dive more deeply into it, the references should be treated as further reading. And thank you very much. Some of the events go back 50 years. Some of you may not have lived through this stuff. So if you want to dive more deeply into it, the references should be treated as further reading. And thank you very much.
Hello. Now we get some feedback here. Hey Jeff.
Hi there.
Could you do us a favor and use only a single device? So the same device that does the playback should also do the recording, so that it can cancel it out, and we don't get feedback.
Okay. Okay. think I'm only using a single device. Oh dear.
Do you have the
I've got some speakers here. Let me see if I can turn those off. Okay, is that better?
perfect?
Okay, when I muted that, then I couldn't hear you. But I've turned down the volume. Let's see. Is that better?
Do you have YouTube open on the other?
This is all being done on my Mac.
Yeah. Still, so if you have YouTube open at the same time, please close that so that you only have audio from us in Google Meet. Thank you.
Got it. Sorry.
Okay. Let's see again. Can you hear myself a bit? I guess we gotta deal with that.
I think we're doing better.
All right. So yeah. Does anyone have any questions? If so, please come here.
Okay, so my question might seem pretty obvious. You ended the talk with "We must defeat Git." I don't know. Must we?
Well, that's my feeling. There's obviously a lot more to be said about that. I think Git is a really lousy version control system and very bureaucratic and unpredictable. And the bigger problem, though, really is that it enables this idea that you can have a bunch of people working on a single program and sort of almost randomly combine change sets, and voila, you get a working correct program that does what you intended. And I've never agreed with that. Some people may get lucky and it works for them. I just don't trust the result of that.
All right, so one question from me and one question from the internet. First one, if I wanted to poke through your changes and maybe pick through and decide which ones I like, where would I go find them?
Probably Nine Legacy for some of them, and I would speak with Adrian Gore. I believe are you in the audience, Adrian? Well, I think he's listening in remotely. Yeah, I have not made a point of breaking it out as individual patches.
Being available somewhere on the internet would be useful.
The tree is available. I can publicize that somewhere. Not sure.
That would be wonderful.
Sorry?
That would be wonderful. Oh, go ahead.
Sorry, just going to add, Adrian's trying to produce a somewhat more, I don't want to say stable, well, shaken down version of my tree. I mean, my stuff works fine for me, but I can't try it on everybody's hardware. So he's doing some of that, and upgrading some of the cryptography.
Okay, and the internet question. I noticed there was no mention of 9front. Any thoughts on that?
Don't know a whole lot about it. No, not really.
Right, well, questions are coming.
What hardware do you recommend for actually trying out the RISC-V port?
I've been using the Star 5 Vision 5 2 pretty successfully. The 2 is significant. Sorry?
I actually have one of those, so where is the software for that?
It's available on my website. I think if you just go to collier.net/who/Jeff/9, there's a pointer to it. There's a whole tree with compilers and the kernel source and the works.
Okay, cool.
Hi. You said the historical tree has like private data in it. Is it like only in the home directories, or are there private data somewhere else?
I'm sorry, I had a little trouble understanding you.
Sorry. So the historical, like from 1990, you said you cannot share it because some private data is sleeping there. Is the private data limited to the home directories, or did it somehow slip somewhere else in the source?
There are a lot of things. Home directories are the obvious one. We also, though, have some proprietary source. There were things that Bell Labs licensed from other places. There are some things I'm not really sure of the licensing state of. I mean, it's just everything. And I would want to do a legal review, I think, before releasing any bits of it. People have asked on occasion for a little, subtrees like their own home directories, and I found ways to make those available. But I don't really see a good way to make the whole thing available. Sorry.
Understand now, because there is this initiative called Software Heritage, and I think they would be quite interested in saving that for future historians. So
I'm aware of the Unix Heritage people. Is this a different effort?
Yeah, it's similar. So the Unix Historical Society is one thing, and then you have like a more generic movement of software preservation called Software Heritage Foundation. And they would, like, for example, archive all of GitHub and make sure that the source is still available, like in 50 years. Yeah.
Right. To that end, the Plan 9 Foundation has got the major releases. So that stuff at least will be available, I hope, indefinitely.
Thanks.
Right, yeah, looks like that's it. And yeah, thank you a lot again. I think everybody enjoyed getting to learn a bit more about the history here. And we will also make sure that you will get this year somehow. I guess you get another round of applause. Yeah, we're making sure that we send this here to you somehow. Oh, right. Yeah, you can't see it right now because it's only on the recording. Anyway, yeah, you will also get a little 3D printed blender.
Thank you.
All right. Thank you.
Okay.
Okay, yeah, we're closing the Google Meet now.
All right.
Yeah, to everyone following online, we're concluding this day now. I'm terribly sorry for the audio network issues that were interfering with us. I hope it will be a bit better tomorrow. We learned a few things. I can't fix everything in the audio, but got a bit better over time. And yeah, have a good one. See you tomorrow.